Have you ever found yourself lying beneath the vast, shimmering tapestry of the night sky, your thoughts drifting beyond the twinkling stars, wondering what hidden dangers lurk silently in the depths of space? What terrifying secrets does the universe conceal, patiently waiting for humanity to stumble upon them? What happens when the unpredictable, chaotic forces of the cosmos suddenly collide with the fragile and delicate sphere we call Earth? These are not mere questions for idle curiosity, but profound mysteries that pull at the very core of our existence, urging us to look up with both awe and apprehension. Join us on a journey as we delve deep into these cosmic enigmas, uncovering some of the most chilling phenomena that space has to offer, exploring the dark and unsettling threats that hover at the edges of our understanding. Imagine for a moment a black hole, an object so dense and gravitationally powerful that it can swallow entire stars, beginning a slow, ominous drift toward our solar system. The story of this cosmic interloper's approach would unfold across millions of years, starting subtly and escalating to unimaginable devastation. At first, the black hole's presence would reveal itself in the faintest disturbances. Scientists would notice small, strange shifts in the orbits of distant icy bodies and comet clouds residing in the dark fringes of our solar system, such as the Kuiper Belt or the Oort cloud. These distant objects would begin to deviate slightly from their long-established paths, nudged by the invisible pull of the approaching black hole's overwhelming gravity. As the black hole draws ever closer, its gravitational grip would intensify, tugging with growing insistence on the farthest planets. The orbits of Neptune, Uranus, and even Saturn would become warped and erratic, creating ripples of chaos that slowly propagate inward. This gravitational turmoil would disrupt the delicate cosmic choreography that keeps our solar system stable. The planets would begin to drift unpredictably, their orbits stretching from gentle ellipses into dangerous, unstable trajectories. Earth itself could face drastic climatic shifts, tidal forces increasing ocean tides to monstrous heights, and atmospheric disruptions, triggering catastrophic weather events. The planet's geological heart might respond violently, with increased volcanic activity and seismic upheavals as the internal pressures shift. If this celestial menace advanced closer still, its impact would spiral into catastrophe. Outer planets might be ripped from their orbits, hurled like cosmic missiles into the void of interstellar space, or swallowed by the black hole's insatiable maw. Closer to home, Earth could be subjected to tidal forces so extreme they would stretch and distort its shape. The very crust of the planet might fracture under these colossal stresses, unleashing earthquakes and reshaping continents. If the black hole approached close enough to our sun, the star at the center of our solar system could be ripped apart, its fiery gases spiraling inward to form a searing accretion disk around the black hole. This maelstrom of energy would bathe the remnants of our solar neighborhood in intense radiation, extinguishing the familiar glow of sunlight and heralding the end of life as we know it. Such a scenario marks a catastrophic and nearly unfathomable conclusion to the cosmic order we depend on. The destructive power of a black hole extends beyond just planets. A star venturing too close risks annihilation through a violent process known as tidal disruption. As the star enters the black hole's tidal radius, the difference in gravitational pull between the star's near and far sides becomes extreme. This gravitational disparity stretches the star into a long, thin filament in a process scientifically referred to as spaghettification. This macabre name evokes the visual of the star's matter being pulled into a gossamer strand of glowing gas, elongated by forces so intense that no part remains intact. This stellar spaghetti eventually spirals into the black hole, heating up tremendously as gravitational energy converts into searing heat and intense radiation. Observers from Earth might witness this as a brilliant flare of X-rays or gamma rays, a cosmic scream signaling the obliteration of a star. In astronomical terms, this grim spectacle can unfold in weeks or months, ultimately erasing the star's existence and feeding the ever-growing black hole. Despite the dramatic and terrifying nature of black holes, the chances of Earth ever encountering a rogue black hole, a black hole wandering aimlessly through space, unbound to any galaxy, are extraordinarily small. Our galaxy alone, the Milky Way, may host millions of black holes, yet these entities occupy an incomprehensibly tiny volume within the vast, dark expanses of space. The closest known black hole, V6116 Monocerotis, lies about 3,000 light-years away, a distance so immense that the likelihood of it drifting near Earth anytime soon is effectively zero. Black holes themselves are invisible, emitting no light, detectable only by the subtle gravitational effects they exert on nearby stars and gas clouds. This invisibility adds to their mystique and fearsome reputation, making them appear as cosmic phantoms lurking just beyond our perception. The concept of spaghettification, the extreme stretching and squeezing of objects as they are drawn toward a black hole, is a vivid and haunting image. This phenomenon arises from the immense tidal forces near a black hole, where gravity's strength varies drastically over tiny distances. For any object or person approaching the event horizon, the difference in gravitational pull between the nearest and farthest parts of the body becomes catastrophic. If a human were to fall feet first into a black hole, the gravity at their feet would be so much stronger than at their head that they would be stretched into an impossibly long, thin shape, reminiscent of strands of spaghetti. This gruesome stretching continues relentlessly until the object is torn apart at the atomic level, its constituent particles spiraling helplessly into the black hole's core. This fate is not limited to humans or spacecraft, but applies to stars and asteroids alike, explaining why the accretion disks around black holes shine so brightly with hot, glowing gas. Black holes trap light itself, a fact that defies our everyday experience of the universe. Their immense mass, compressed into an unimaginably small volume, creates a gravitational field so powerful that it warps space and time itself. According to Einstein's theory of general relativity, gravity arises from the bending of space-time by mass. A black hole's gravity curves space-time to such a degree that even light, the fastest thing in the universe, cannot escape once it crosses a boundary known as the event horizon. This boundary is the point of no return. Beyond it, escape is impossible, and matter is inexorably drawn inward toward the singularity, a region of infinite density where current physics breaks down. Because black holes emit no light and reflect none, they appear utterly black against the backdrop of space. Detecting them requires observing their gravitational influence on nearby stars or the energetic emissions from matter heated as it falls into the black hole. Occasionally, black holes announce their presence through gravitational waves, ripples in space-time generated when two massive objects, such as black holes, collide and merge. These cosmic events, first predicted by Einstein and only recently observed by detectors like LIGO, release vast amounts of energy, equivalent to several suns being converted into gravitational wave energy in moments. When two black holes spiral into one another, they perform a gravitational dance, losing orbital energy as they emit increasingly powerful gravitational waves. Their final collision produces a new, larger black hole and a spectacular outburst of space-time ripples that spread across the cosmos. The detection of these waves not only confirms fundamental physics theories, but opens a new window for observing the universe, revealing phenomena invisible through traditional telescopes. Each of these cosmic horrors, from the silent approach of a rogue black hole to the violent death of a star through spaghettification to the faint whispers of gravitational waves from black hole mergers, reminds us how fragile our place in the universe truly is. These forces are beyond human scale, existing in realms where the known laws of physics strain and sometimes fail. As we continue to peer deeper into space and time, our understanding of these dangers grows, but so too does our sense of wonder and humility before the immense and mysterious cosmos that surrounds us. Have you ever looked up and felt both fascination and fear? These cosmic tales are not just stories, they are real, terrifying realities of the universe we inhabit. But slightly less than their combined mass due to the energy radiated away, the story of black hole mergers unfolds as one of cosmic drama and fundamental revelation. These extraordinary events, invisible in ordinary light, whisper through the universe in the language of gravitational waves, ripples in the fabric of space-time, traveling vast distances, carrying with them secrets from the darkest and most extreme corners of existence. These detections of gravitational waves have revolutionized astrophysics, providing scientists with a new cosmic lens. For the first time, we can listen to the universe's hidden symphony, capturing echoes of cataclysmic black hole collisions. These signals offer unprecedented insights into the properties, behaviors, and origins of black holes, validating Albert Einstein's predictions made over a century ago and breathing life into his theory of general relativity. Einstein's framework imagined gravity not as a mere force, but as the bending and warping of space-time itself, a four-dimensional fabric that curves around massive objects like planets, stars, and black holes. Imagine a heavy ball placed on a trampoline. Its weight causes a dip, a distortion in the fabric. When these massive objects move violently or merge, they send waves radiating outward, ripples that stretch and compress space-time itself, known as gravitational waves. When two black holes become entwined in their mutual gravitational dance, spiraling ever closer, they lose energy by emitting these waves. Their orbit shrinks, the speed of their dance increases, and the gravitational waves grow in strength and frequency. Near the climax of this cosmic ballet, the black holes collide and merge in a cataclysmic event, unleashing a sudden massive burst of gravitational waves that race through the universe at light speed. This titanic explosion of energy shakes the very fabric of space-time, spreading disturbances that can be detected here on Earth. Specialized instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo are designed to catch these elusive signals. Using laser interferometry, these detectors measure unimaginably tiny shifts, fractions of the width of a proton, in the distance between mirrors separated by kilometers. The passing gravitational waves stretch and compress space itself, revealing their presence in the subtle dance of laser beams. These detections not only confirm the dynamic, ever-changing nature of space-time, but also open a new era of observational astronomy. Unlike traditional telescopes that rely on electromagnetic radiation such as light or radio waves, gravitational wave detectors allow us to hear cosmic events that were once hidden, black holes merging far beyond the reach of visible observation. By analyzing these waves, scientists can deduce the mass, spin, and distance of the merging black holes, unraveling the story of their violent union and the cosmic evolution tied to these phenomena. These mergers are thought to play a critical role in the formation and growth of galaxies, influencing the grand architecture of the universe. As black holes coalesce, they sculpt their surroundings, affecting the behavior of stars and gas clouds, driving the cosmic evolution that leads to the diverse galaxy shapes and structures we observe today. If Earth were to encounter a black hole's event horizon, the ultimate boundary beyond which nothing can escape, the consequences would be nothing short of catastrophic and terminal. The event horizon acts as a point of no return, a cosmic threshold where the pull of gravity becomes so intense that even light cannot flee. As Earth approached this boundary, the immense gravitational forces would begin to tear it apart. Initially, the side of Earth closer to the black hole would experience a stronger gravitational tug than the far side, creating what is known as tidal stretching. This effect is a far more intense version of the tidal forces we experience from the moon's influence on our oceans. These differential forces would stretch Earth into an elongated shape, distorting the planet until the forces became overwhelming. As the planet neared the event horizon, tidal forces would increase dramatically, eventually overcoming the structural integrity of Earth itself. This violent process, known colloquially as spaghettification, would elongate and pull Earth apart, atom by atom, strand by strand, until it was torn into thin filaments of matter. Once any part of Earth crossed the event horizon, it would be drawn inexorably inward toward the black hole's singularity, a point of infinite density where the known laws of physics cease to apply. Matter would be crushed and compressed beyond recognition, losing all familiar structure and form. The immense energies unleashed during this catastrophic destruction would contribute to the glowing accretion disk around the black hole. This disk of superheated gas and debris emits powerful X-rays and other forms of high-energy radiation, illuminating the surroundings in eerie, intense light. For any human or living being approaching the event horizon, survival is impossible. The overwhelming gravitational forces would instantly end all life and matter, making any close encounter terminal. Fortunately, the likelihood of Earth encountering a black hole remains extraordinarily low. with such events confined to the distant realms of space and cosmic time. Yet, through the detection and study of gravitational waves, humanity has unlocked a new chapter in cosmic exploration. We now listen to the rhythms of the universe's most violent and mysterious events, gaining profound understanding of gravity, black holes, and the dynamic nature of the cosmos itself. These discoveries continue to reshape our view of reality, pushing the boundaries of knowledge toward realms once thought forever beyond reach. But it underscores the awe-inspiring yet fundamentally destructive essence of these cosmic titans: black holes. These enigmatic entities, shrouded in mystery and wrapped in the fabric of space-time, can unleash some of the most cataclysmic phenomena known to the universe: deadly gamma-ray bursts, or GRBs. These bursts are not mere flashes of light, but titanic explosions that outshine entire galaxies, moments when the cosmos reveals its raw explosive power. Gamma-ray bursts emerge during profoundly dramatic cosmic episodes, especially when black holes are born or engage with other celestial bodies. They represent the most powerful explosion since the dawn of the universe, is capable of releasing in mere seconds as much energy as our sun will radiate over its entire lifespan of roughly 10 billion years. Such bursts ripple through the universe as blinding, energetic waves, signaling violent transformations in deep space. There are two primary scenarios in which black holes give rise to these ferocious bursts of gamma rays. The first is the collapse of a massive star in a supernova, a spectacular stellar death that sets the stage for black hole birth. Imagine a giant star, many times the mass of our sun, exhausting its nuclear fuel. Without the outward pressure from fusion to counteract gravity, its core succumbs, collapsing inward in a fraction of a second. This implosion sends shockwaves through the star's outer layers, blasting them violently into space. During this chaotic demise, if conditions align perfectly, twin jets of relativistic particles ignite along the star's spin axis. These jets, traveling at near light speed, slice through the dying star's remnants and burst out into the void, unleashing an intense gamma-ray burst. These long-duration bursts can persist from a few seconds up to several minutes, painting the cosmos with powerful flashes of energy that signal a black hole's birth in the wake of stellar collapse. The second dramatic genesis of gamma-ray bursts lies in the cosmic dance of death between two neutron stars, or a neutron star and a black hole. Neutron stars, themselves remnants of supernovae, are incredibly dense, packing the mass of a sun into a sphere no larger than a city. As these compact objects spiral closer, gravitational waves ripple through space-time, draining their orbital energy. Eventually, they collide with unimaginable force. This collision unleashes an intense burst of energy in a very short time, typically less than 2 seconds, creating what is known as a short-duration gamma-ray burst. In the chaos following the collision, a swirling accretion disk forms around the newborn black hole. Magnetic fields twist and channel some of this material into narrow, focused jets that emit gamma rays, piercing through the fabric of the universe like cosmic lighthouses. Both scenarios, stellar collapse and compact object mergers, give birth to black holes and generate extreme environments where these powerful jets form. The creation of these jets hinges on the interplay between gargantuan magnetic fields and the staggering rotational energy of the collapsing or merging bodies. As these jets blaze outward at nearly the speed of light, orbiting observatories like NASA's Fermi Gamma Ray Space Telescope capture their signals, offering humanity precious insights into the mechanics behind black hole formation and the violent, dynamic processes shaping our universe. If such a gamma ray burst were aimed directly at Earth, even from thousands of light years away, the consequences could be catastrophic. The tense burst could strip away Earth's protective ozone layer, exposing the surface to lethal levels of solar and cosmic radiation, potentially devastating all life forms. Fortunately, given the vastness of the cosmos and the rarity of these precisely targeted bursts, the probability of Earth facing such a direct hit remains vanishingly small. Yet, the importance of studying these phenomena remains paramount, as they unravel secrets of stellar evolution, black hole birth, and the nature of extreme physics. Turning to a different class of black holes, micro-black holes, or primordial black holes, are a fascinating theoretical possibility. Unlike the massive black holes born from dying stars, these miniature black holes could be tiny, possibly as small as subatomic particles. Some theories propose their formation in the earliest moments of the universe, moments after the Big Bang. In that chaotic, high-energy environment, regions of spacetime could have been squeezed to such extremes that compact objects formed directly, independent of stellar evolution. These micro-black holes could have masses akin to a mountain compressed into a volume smaller than a proton, an almost unimaginable density. What makes micro-black holes particularly intriguing is their predicted relationship with Hawking radiation, a phenomenon proposed by physicist Stephen Hawking. Hawking radiation suggests that black holes are not entirely black. Quantum effects near their event horizons cause them to emit particles, slowly losing mass over time. The smaller the black hole, the more rapidly it radiates and evaporates. This means micro-black holes could disappear entirely, releasing bursts of energy as they vanish. Regarding the danger posed by micro-black holes, the scientific consensus is reassuring. Their minuscule size and rapid evaporation due to Hawking radiation imply they would pose little to no threat to Earth. Instead, if they exist, they may offer a unique window into quantum gravity and the earliest epochs of our universe's history. Thus, from the titanic gamma-ray bursts marking the violent birth of stellar black holes to the elusive whisper of Hawking radiation from micro-black holes, these cosmic enigmas highlight the profound extremes of nature. Their study not only expands our understanding of the universe's most violent processes, but also challenges our comprehension of physics at the furthest edges of knowledge, but not enough to cause significant harm on a cosmic scale, even if micro-black holes were produced in high-energy experiments such as those conducted at the Large Hadron Collider, or LHC. The prevailing scientific expectation is that any micro-black holes formed in such environments would evaporate almost instantaneously through a process known as Hawking radiation, posing no real danger to their surroundings. The energies involved in these experimental setups, although immense by human standards, remain far lower than those that existed mere fractions of a second after the Big Bang. This disparity makes the spontaneous creation of stable micro-black holes in laboratory conditions exceedingly improbable. Nevertheless, the pursuit of understanding micro-black holes holds substantial value for theoretical physics. These hypothetical entities provide a unique window into the interplay between gravity and quantum mechanics, two pillars of physics that traditionally resist unification. Micro-black holes, if ever observed, could offer crucial insights into the very fabric of space-time itself, challenging or confirming the boundaries of our current understanding. By exploring these exotic objects, scientists are able to test the limits of established theories, pushing forward the frontiers of knowledge regarding the universe's most fundamental principles. When two galaxies collide, the event unfolds not as a sudden, violent crash, but rather as an awe-inspiring cosmic ballet that stretches over hundreds of millions to billions of years. Contrary to the dramatic connotations evoked by the word collision, the vast expanses between stars within these galaxies mean that direct stellar collisions are exceedingly rare. Instead, what transpires is an intricate gravitational interaction that profoundly reshapes the structure and destiny of both galaxies involved. As the galaxies draw nearer under the irresistible pull of their mutual gravity, their shapes become distorted by intense tidal forces. These forces stretch and warp the galaxies, often creating spectacular elongated streams of stars and gas known as tidal tails, which arch far into intergalactic space like cosmic ribbons. The tumult of gravitational forces compresses vast clouds of gas, triggering explosive bursts of star formation. These stellar nurseries ignite, flooding entire regions with brilliant new stars clustered tightly in youthful, radiant groups. At the core of nearly every large galaxy lies a supermassive black hole, a mysterious gravitational anchor millions to billions of times the mass of our Sun. When two galaxies merge, their central black holes embark on a slow, inexorable dance, spiraling closer until they eventually coalesce into a single, even more massive supermassive black hole. This monumental union sends ripples through space-time in the form of gravitational waves, subtle but powerful distortions that traverse the cosmos, enriching its dynamic fabric. The chaotic gravitational forces unleashed during the merger also fling stars into new, sometimes wildly eccentric orbits. Some stars gain enough velocity to be ejected entirely from their galactic homes, becoming rogue stars wandering alone through the vast emptiness of intergalactic space. Over time, the two galaxies settle into a new, more stable configuration. Depending on their original masses and structures, the resulting galaxy may take dramatically different shapes. For example, the merging of two spiral galaxies often yields an elliptical galaxy, characterized by a smooth, spheroidal form rather than defined spiral arms. Our own Milky Way galaxy is on a slow-motion collision course with its nearest large neighbor, the Andromeda Galaxy. This epic encounter is projected to unfold approximately 4 billion years from now. When the moment arrives, the two galaxies will begin their gravitational dance, circling and weaving around each other before finally merging into a single colossal galaxy, affectionately nicknamed Milkometa by astronomers. The consequences of this cosmic event will dramatically reshape the fate of both galaxies, offering a unique natural laboratory to study galactic evolution, star formation, and the enigmatic behavior of supermassive black holes. These galactic mergers stand among the most magnificent and transformative phenomena in the universe. Their grandeur lies not only in their scale, but also in their ability to leave indelible marks on the structure and contents of the galaxies involved. They are cosmic sculptors, molding the architecture of the universe itself over eons. A massive asteroid impact, on the other hand, could unleash destruction on a much smaller, yet far more immediate scale. The potential for such an event to extinguish life on Earth lies in the cascade of catastrophic consequences it would trigger. Upon impact, the energy released would be astronomical, comparable to the simultaneous detonation of several billion nuclear bombs. This tremendous force would manifest as blistering heat, powerful shock waves, and intense seismic activity, enough to cause widespread devastation across the planet's surface. The initial blast would obliterate anything within the immediate vicinity, vaporizing landscapes and igniting vast wildfires that could spread uncontrollably. Shockwaves would travel through the Earth's crust, triggering earthquakes and volcanic eruptions in regions far from the impact site. As dust and debris are hurled into the atmosphere, they would block sunlight, plunging the planet into a nuclear winter scenario where global temperatures drop sharply. This drastic cooling would disrupt ecosystems, collapse food chains, and cause widespread extinction. Over weeks, months, and even years, the environmental aftermath would persist, reshaping the biosphere and forcing surviving species to adapt to radically altered conditions. The fossil record bears witness to such cataclysmic impacts in Earth's deep past, with the most famous being the event that ended the reign of the dinosaurs 66 million years ago. While rare, the threat posed by massive asteroids remains a sobering reminder of the fragile balance that sustains life on our planet, highlighting the need for vigilant monitoring of near-Earth objects. Through understanding both the grand cosmic events like galactic collisions and the more immediate planetary threats, such as asteroid impacts, humanity gains perspective on its place within the universe. These phenomena, vast in scale and consequence, underscore the dynamic and ever-changing nature of the cosmos, where creation and destruction dance in an endless cycle. They invite us to explore, to marvel, and to prepare for the mysteries and challenges that lie ahead in the unfolding story of existence. And so it begins with a cosmic juggernaut hurtling through the void of space, a colossal asteroid on a collision course with Earth. The impact, an explosion of unimaginable force, would tear into the surface of our planet, gouging out a massive crater hundreds of kilometers wide. The initial blast would pulverize everything near the impact site, turning solid rock into molten lava and sending a vast plume of dust, ash, and debris high into the atmosphere. In the immediate vicinity, the violence would be apocalyptic. Infernos ignited by searing heat would engulf forests and cities alike, winds surpassing hurricane strength would roar outward, and monstrous tsunamis would surge across oceans if the impact struck a watery realm. Yet these immediate horrors, while catastrophic, pale in comparison to the insidious aftermath that would envelop the globe in darkness and cold. For the real menace lies not merely in the shock and fire, but in the skies above, where a thick veil of dust and aerosols would linger, suspended in the stratosphere, blotting out the sun's life-giving rays. This celestial shroud, forged from pulverized rock and vaporized minerals, would drastically reduce solar radiation reaching Earth's surface, triggering a phenomenon scientists call an impact winter. The sun would become a faint, distant glow behind curtains of choking haze, and global temperatures would plummet in a chilling embrace that could last months or even years. This frigid darkness would starve the planet's ecosystems at their very roots. Photosynthesis, the process by which plants and microscopic oceanic phytoplankton convert sunlight into energy, would falter and ultimately collapse. Without sunlight, these primary producers, the foundation of the entire food web, would die off en masse. From the tiniest phytoplankton drifting in the oceans to vast forests sprawling across continents, the loss would cascade through the biosphere. Herbivores deprived of vegetation would face starvation, and the carnivores that rely on them, humans included, would struggle to survive amid widespread food shortages. The planet's intricate and delicate balance would unravel, threatening extinction on an unparalleled scale. But the catastrophe would not stop there. The impact would also vaporize sulfur-rich rocks, releasing sulfur compounds into the atmosphere. These gases would combine with atmospheric moisture to spawn acid rain, a toxic downpour that would poison freshwater sources and degrade soil fertility. This chemical assault would compound the challenges faced by surviving species, further destabilizing ecosystems already reeling from cold and starvation. Across the world, rivers and lakes would become corrosive traps, and the soil itself would become inhospitable to regrowth, delaying any hope of ecological recovery. Throughout Earth's deep history, evidence of such cataclysms has been etched in the geological record. The most famous instance occurred approximately 66 million years ago, when an asteroid, roughly 10 kilometers in diameter, struck the Yucatan Peninsula. This event is widely credited with triggering the Cretaceous-Paleogene extinction, a mass extinction that eradicated about 75% of all species on Earth. Among those lost were the non-avian dinosaurs, once the dominant terrestrial vertebrates, alongside countless other plants and animals. The scars of that impact still speak to us through the iridium-rich layers in rock and the massive crater known as Chicxulub, a silent testament to nature's destructive power. Today, humanity watches the heavens with wary eyes. Through a network of telescopes and space agencies, near-Earth objects, asteroids, and comets that cross Earth's orbit are continuously tracked. This vigilance offers some reassurance, an early warning system that could someday give humanity precious time to prepare or divert a potential impactor. Yet despite our efforts, the sheer scale and suddenness of such an event underscore a terrifying truth. Our planet remains vulnerable to the caprices of the cosmos. Equally awe-inspiring and terrifying are the gamma-ray bursts, or GRBs, explosive cosmic phenomena far more energetic than any asteroid impact. These bursts unleash torrents of gamma radiation, the highest energy form of electromagnetic radiation, in blinding flashes that can outshine entire galaxies for fleeting moments. The energy discharged in a few seconds by a GRB can match the output of the sun across its entire 10 billion year lifespan, a testament to the staggering forces at work in the universe. GRBs originate from catastrophic celestial events, the death throes of massive stars collapsing into black holes, or the violent merger of neutron stars, the dense remnants of exploded stars packed with matter so compact that a teaspoon weighs billions of tons. These events spawn narrow, focused jets of particles moving at near-light speed, which emit intense gamma rays when they collide with surrounding material. Astronomers classify GRBs into two main types: long-duration bursts lasting more than 2 seconds, generally linked to massive star collapses, and short-duration bursts under 2 seconds, often caused by neutron star mergers. If such a burst were to occur nearby in our cosmic neighborhood, and if one of its lethal jets pointed directly at Earth, the consequences could be apocalyptic. The initial wave of gamma radiation would tear into our atmosphere, ionizing molecules and driving chemical reactions that produce nitrogen oxides. These compounds catalyze the destruction of ozone, the fragile atmospheric layer that shields life from harmful ultraviolet radiation. Without the ozone's protective embrace, UV rays from the sun would bombard the surface, wreaking havoc on DNA molecules and triggering lethal mutations in countless organisms. from the plankton that support marine food webs to land plants and animals, including humans. In the wake of the gamma-ray burst, the atmosphere would not simply recover. The nitrogen oxides and other reactive chemicals would persist, darkening skies with nitrates that could seed acid rain and initiate a gamma-ray burst winter. This phenomenon would mirror the impact winter caused by asteroid collisions, plunging the Earth into a prolonged period of intense cold and environmental stress. Life as we know it would face a brutal test against radiation, freezing temperatures, and collapsing ecosystems. Thus, the cosmos, in its vastness and violence, harbors forces beyond human control or full comprehension. Asteroids that smash into worlds and gamma-ray bursts that unleash celestial fury. Both remind us of the fragile thread by which life hangs on Earth, and the urgent need for vigilance and scientific advancement to better understand, prepare for, and perhaps one day shield ourselves from these cosmic threats. And this cooling, so sudden and intense, could replicate the dire aftermath of a nuclear winter. A steep global plunge in temperature would sweep across continents, destabilizing climates, dismantling fragile ecosystems, and sparking widespread food crises. History, etched into layers of sediment and extinction markers, whispers of similar catastrophes that may have been sparked by distant cosmic triggers. Although science has yet to find irrefutable proof, the fingerprints of ancient gamma-ray bursts linger in the geological record like shadows from forgotten disasters. Fortunately, gamma-ray bursts, or GRBs, are vanishingly rare and tend to erupt in galaxies far removed from our own. Their odds of directly impacting Earth are exceedingly small. Yet, their very existence commands our attention, because even from across the void, they serve as ominous reminders of the existential threats that loom silently in the cosmos. Vigilance, through telescopes and time, becomes our first defense. But GRBs are only one chapter in a larger, more explosive cosmic narrative. Imagine a massive star nearing the end of its life, a stellar titan collapsing under its own gravity. In an instant, it detonates in a supernova, releasing more energy than our sun will in its entire 10 billion year lifespan. This violent spectacle hurls vast amounts of matter and radiation into the interstellar medium, rewriting the environment around it in every direction. For any planet caught too close, the consequences are unforgiving. The blast floods nearby space with lethal radiation, gamma rays, X-rays, and ultraviolet light. These waves can strip planetary atmospheres in moments. Without its atmospheric shield, a planet is laid bare, scorched by radiation, vulnerable to cosmic and solar onslaughts. Life, as we understand it, would stand little chance. Mars offers a sobering example. While it lost much of its atmosphere through slower, less violent means, the result is clear: a dry, irradiated world, inhospitable to complex life. Now imagine that multiplied on a cosmic scale by the detonation of a nearby star. And radiation is only the beginning. High-energy cosmic rays, the subatomic debris of supernovae, travel across galaxies. These particles pierce atmospheres and biological tissue alike, mutating DNA and, in sufficient doses, sterilizing entire biospheres. For planets exposed to prolonged bombardment, survival becomes statistically improbable. Then comes the shockwave. A blast of matter and energy racing through space at tens of thousands of kilometers per second. If a planet lies within just a few light years, this wave could compress its atmosphere, triggering cataclysmic heating or atmospheric loss. Climate systems would be torn asunder. Entire environments could be rendered unrecognizable in moments. Supernovae don't just destroy, they reshape. The explosion releases heavy elements: carbon, oxygen, iron. These are the seeds of life, flung into the galaxy to become the raw material of future stars, planets, even potential civilizations. This duality, creation born of destruction, is the paradox of stellar death. But for any world too close to witness it directly, creation is not on the agenda. Survival isn't either. While no nearby stars are expected to go supernova in our cosmic backyard anytime soon, studying these celestial detonations grants us invaluable knowledge. We begin to understand the cycles of star birth and death, the vulnerabilities of planetary environments, and the precarious thread on which life dangles in the universe. Now, picture a different yet equally terrifying dance. A neutron star, a dense stellar remnant with the mass of the sun compressed into a sphere the size of a city, drifts toward its doom. Its partner, a black hole, a gravitational monster from which nothing can escape. As they spiral inward, the fabric of space-time itself begins to shudder. This cosmic duet is no silent performance. It crescendos into a gravitational wave, ripples in space-time, racing across the cosmos, reaching detectors like LIGO and Virgo on Earth. We listen, we record, and in those moments we eavesdrop on the universe itself. And yet, in the dark theater of the cosmos, few spectacles rival the ferocious ballet between a neutron star and a black hole. Drawn into the black hole's gravitational snare, the neutron star spirals ever inward, gripped by tidal forces so intense they warp its shape beyond recognition. It stretches, twists, becoming an elongated strand of celestial matter, eerily reminiscent of a cosmic spaghetti noodle. As the neutron star nears its doom, its outer layers begin to peel away, torn off by sheer gravitational brutality. This stolen matter doesn't simply vanish, it spins into a searing accretion disk around the black hole, heating to millions of degrees. The result is an invisible scream across space, torrents of X-rays, so powerful they can be seen across billions of light years. Then, with terrifying swiftness, the finale unfolds. The neutron star, already broken and scattered, plunges into the waiting maw of the black hole. The merger is a moment of titanic violence, an astronomical collision that sends ripples through the very fabric of space-time. These gravitational waves, faint but unmistakable, surge outward, whispering their story to instruments like LIGO and Virgo. What they reveal is not just the collision itself, but insights into the most extreme physics in existence, the rules that govern matter under infinite pressure and time warped by gravity. Meanwhile, another cosmic drama plays out closer to home. Picture a lonely traveler, a comet, hurtling toward Earth from the far reaches of the solar system. Its journey is ancient, forged in the icy outskirts of the Kuiper Belt or even beyond. But as it approaches our planet, its icy heart races forward at speeds exceeding Mach 20, transforming into a blazing fireball upon contact with our atmosphere. This isn't just a shooting star, it's a celestial warhead, potentially kilometers wide, carrying the destructive power of millions of atomic bombs. When such a comet strikes Earth, the outcome is apocalyptic. The energy released upon impact is enough to vaporize both the comet and a massive swath of the Earth's crust, leaving behind a crater that may span hundreds of kilometers. But the true devastation lies not in the crater, it lies in the sky. Gigantic plumes of ash and debris are thrown into the atmosphere, forming a choking veil that dims the sun. In this unnatural night, photosynthesis grinds to a halt, plunging global ecosystems into chaos. From microscopic algae in the seas to towering dinosaurs on land, entire food chains unravel. Firestorms rage, acid rains fall, and temperatures drop in a planetary cold snap known as an impact winter. This chain of catastrophe is not theoretical, it happened. Around 66 million years ago, the Chicxulub impact sealed the fate of the non-avian dinosaurs, ending an era in Earth's deep past. That single event reshaped life itself. But space has not stopped sending messengers. In late 2017, astronomers caught a glimpse of something wholly unexpected. Oumuamua, an object not from our solar system, but from the yawning depths of interstellar space. Unlike any comet or asteroid previously recorded, Oumuamua moved on a hyperbolic path, one that ensured it would visit just once, never to return. It didn't behave like a typical comet. It lacked a tail, spun oddly, and accelerated in ways we still don't fully understand. Its visit was fleeting, mere weeks from first detection to its silent departure. But what it left behind was a chilling realization. We are not as prepared as we think. Interstellar objects like Oumuamua are ancient relics, fragments of other star systems wandering the galaxy. They may contain alien materials, unseen isotopes, or even unimagined structures. And because of their speed and erratic courses, they offer us precious little time to react. Though Oumuamua was harmless, others may not be. What if the next interstellar visitor isn't a passive wanderer, but a harbinger of disaster? Our current detection systems may not offer enough warning. In the face of these celestial unknowns, humanity must ask, are we ready? And yet, we often forget how fragile our cosmic perch truly is. These interstellar wanderers, rogue stars and supernovae, loom like silent sentinels of possibility, moving undetected through the black velvet of space until their influence collides with our reality. To anticipate and withstand such forces, we must develop sharper eyes on the cosmos, more sophisticated astronomical monitoring, early warning systems, and interplanetary preparedness strategies. Because these celestial interlopers are not just abstract dangers, they are real, roaming reminders of the volatile and interconnected universe we inhabit. Picture, if you will, a rogue star, a luminous vagrant adrift in the galaxy, free from any gravitational master. Unlike our sun, which sits serenely at the heart of a well-behaved solar system, these nomadic stars travel with reckless abandon, often at hundreds of kilometers per second. They remind us more than anything that we are not alone on a stable, permanent stage. We are passengers aboard a fragile vessel, sailing through a dynamic and often dangerous sea of stars. And these cosmic collisions aren't just about stars crashing into each other in a blaze of light and heat. No, the real chaos lies deeper, in the invisible grip of gravity itself. As massive galactic structures drift toward one another, their gravitational fields begin a dance of unimaginable violence. These fields distort, intertwine, and erupt with waves of energy that ripple outward at staggering velocities. These are not ripples on a pond. These are gravitational shockwaves, moving like celestial tsunamis through the fabric of space-time, capable of destabilizing entire solar systems in their path. When such a wave collides with a solar system, the consequences are profound. Planets, once locked in the serenity of stable orbits, can be flung into their stars or hurled into the icy reaches of interstellar space as wandering rogues. Asteroids and comets, too, are thrown off course, transformed into cosmic missiles on unpredictable paths. The very winds that cradle a solar system, the solar winds, can be disrupted, breaking the heliosphere's protective shell and exposing planets to a raw barrage of cosmic radiation. This invisible onslaught could destroy the equilibrium necessary for life, unraveling billions of years of gravitational choreography in a matter of moments. Yet out of this turmoil, creation can also arise. The intense energy released in such collisions compresses interstellar clouds of dust and gas, triggering the birth of new stars. But even this process holds a cruel balance. While new stars are born, others are suffocated as their life-giving gases are stripped away. This violent duality of destruction and rebirth is at the heart of cosmic evolution. It reminds us that galaxies are not eternal havens of order, but shifting, volatile arenas where stability is borrowed and chaos is the rule. Imagine now a magnetar, the most magnetic object known in the universe. A rare breed of neutron star, its magnetic field is 1,000 times stronger than that of ordinary neutron stars, and a staggering quadrillion times greater than Earth's. These terrifying remnants are born from the explosive deaths of massive stars. What remains is a city-sized core packed into unimaginable density, its magnetic might so extreme it can twist atomic structures and unleash bursts of X-rays and gamma rays so intense they defy reason. Should one of these entities erupt with a magnetic flare near Earth, the results would be devastating. A magnetic storm of this magnitude could send colossal currents surging through our magnetosphere. Unlike solar flares, which themselves can knock out satellites and power grids, magnetar storms are exponentially more powerful. GPS systems would falter, communications could collapse, satellites might fail en masse, transformers could burn out, darkening entire continents. An intense electromagnetic pulse could fry sensitive electronics in an instant, from hospital equipment to global banking systems, hurling civilization into a technological dark age. While such events are rare, the mere possibility is a sobering reminder of the universe's brutal potential and our fragile dependence on technology. Supernova, colossal detonations that mark the death of massive stars, are among the most energetic events in the universe. When a star 8 times the mass of our sun exhausts its fuel, it collapses under its own weight, briefly giving rise to a neutron star or black hole before violently shedding its outer layers. The resulting explosion can outshine an entire galaxy, releasing more energy in a few months than the sun will emit in 10 billion years. Imagine the sky lit not by a sunrise, but by a star's death seen from light years away, a billion trillion hydrogen bombs exploding in perfect unison. If a supernova occurred within 50 light years of Earth, the implications would be dire. Gamma rays from the explosion could obliterate the ozone layer, exposing our planet to the sun's lethal ultraviolet radiation. Increased UV levels could cripple photosynthesis in plants, disrupt food chains, and cause a global spike in skin cancer. Ionized atmospheric particles would lead to the production of nitrogen oxides, further damaging the ozone and possibly initiating a cooling effect akin to a nuclear winter. Some scientists even speculate that past mass extinctions like the Devonian event 359 million years ago might have been triggered by such explosions, as life forms reliant on sunlight were decimated by elevated radiation. Yet, as terrifying as supernovae are, they pale in comparison to their monstrous cousins, hypernovae. These are the end-of-life events for stars with more than 30 times the mass of the Sun. When such titans die, their cores collapse directly into black holes, and the energy released is nothing short of apocalyptic. In just seconds, a hypernova can produce a gamma-ray burst that emits more energy than our Sun will manage over its entire existence. Should a gamma-ray burst from a nearby hypernova strike Earth, it would be like staring into the barrel of the cosmos itself. The gamma rays would strip away the ozone layer, as in a supernova, but with far more aggression and speed. The high-energy particles that follow would poison the atmosphere, sterilize regions of the surface, and trigger planet-wide environmental collapse. Thankfully, such an event is astronomically rare. But rare does not mean impossible, and the mere existence of hypernovae redefines what we think of as catastrophic. It's not just that we're vulnerable, it's that in the grand scheme of the cosmos, we're exposed. But on an even grander scale, the consequences of such an event would be truly catastrophic, exposing a planet's surface to lethal levels of ultraviolet radiation with devastating effects on every form of life. Furthermore, the barrage of high-energy cosmic rays unleashed would cause intense atmospheric ionization, triggering complex chemical reactions that could plunge the planet into a prolonged and harsh climatic upheaval, what scientists often describe as an impact winter. This chilling scenario isn't just science fiction. Historical studies propose that gamma-ray bursts originating from hypernovae, immense stellar explosions, may have driven mass extinction events on Earth's ancient timeline. Though direct proof remains elusive and largely theoretical, the mere possibility of a hypernova erupting within our cosmic neighborhood represents a profound and ominous threat. Unlike the slow and predictable astronomical changes we observe, the effects of a hypernova would be swift, widespread, and unforgiving. Fortunately, these cosmic cataclysms are exceedingly rare and typically occur millions of light years away from our solar system, offering us a fragile sense of security. Yet, the immense destructive potential they embody serves as a humbling reminder of the universe's vast and unpredictable power, a cosmic force that operates on a scale far beyond human control or understanding. Pulsars, the extraordinary remnants of massive stars that have ended their lives in supernova explosions, provide another stark example of this cosmic dynamism. These neutron stars cram more mass than the Sun into a sphere barely 20 kilometers across, spinning at dizzying speeds, sometimes hundreds of times per second. Their intense magnetic fields channel beams of electromagnetic radiation from their magnetic poles, which sweep across the cosmos like the piercing light of a celestial lighthouse. These beams are no ordinary light. They encompass a wide spectrum of energy, ranging from low-frequency radio waves to highly energetic X-rays and gamma rays. Imagine if one of these pulsar beams were to intersect with Earth. The consequences could be devastating. The relentless onslaught of high-energy particles would ionize the atmosphere, leading to the formation of nitrogen oxides that break down the protective ozone layer. Without this vital shield, harmful ultraviolet rays from the Sun would bombard the surface, threatening to make the planet inhospitable by increasing radiation-induced illnesses and disrupting fragile ecosystems. Beyond the biological impact, the intense radiation could wreak havoc on electronic systems and communication networks, jeopardizing modern technology. Models even suggest that pulsar emissions could sterilize planets close enough, wiping out life regardless of its complexity. While the likelihood of Earth falling directly in the path of a pulsar's beam is incredibly small, the scenario vividly illustrates the immense power and danger lurking within the universe's most fascinating objects. This haunting possibility underscores just how precarious our existence is on this small, fragile blue dot, a mere speck adrift in a cosmos filled with both wonder and existential threat. Quasars stand among the universe's most luminous and energetic phenomena, showcasing the ferocity of supermassive black holes at the centers of distant galaxies. These cosmic titans, with masses millions or even billions of times that of our Sun, voraciously consume surrounding matter. As this matter spirals inward, it forms a superheated accretion disk that shines brilliantly across the electromagnetic spectrum, often outshining the combined light of all the stars in its host galaxy. The energy output from a quasar is almost incomprehensible, frequently surpassing that of a trillion suns. The intense radiation emitted, from radio waves to visible light, ultraviolet rays, X-rays, and gamma rays, can obliterate anything unfortunate enough to be too close. These energetic particles strip electrons from atoms, ionizing and shattering molecular structures over vast distances, sometimes extending several light years. The scorching radiation can sterilize entire planets, stripping away atmospheres and rendering their surfaces utterly uninhabitable. Additionally, quasars unleash colossal jets of energetic particles that can stretch millions of light years, carving cosmic scars and adding to the devastation. Together, these cosmic phenomena, the hypernova, pulsar, and quasar, highlight the universe's immense and unpredictable forces, reminding us of the delicate balance that sustains life on our planet amid the vast, sometimes hostile expanse beyond. These jets, composed of charged particles hurtling through space at nearly the speed of light, unleash torrents of intense radiation and high-energy particles, functioning like a colossal cosmic blowtorch, scorching everything in their path. Far from this furious heart, the radiation from these jets still exerts a formidable influence, heating interstellar gas and halting the birth of new stars. This suppression of star formation acts as a cosmic throttle, stalling the growth of entire galaxies for millions of years. The overwhelming energy output from quasars profoundly sculpts the evolutionary journey of their host galaxies and the surrounding cosmic web, shaping the grand architecture of the universe itself. Meanwhile, Earth remains safely nestled in a quiet, less volatile corner of the cosmos, yet the terrifying power of quasars serves as a stark reminder of the universe's boundless forces, capable of both creation and destruction on unimaginable scales. Imagine then a supernova, the explosive death throes of a massive star, detonating alarmingly close to our solar system. Typically, these cataclysmic events occur hundreds to thousands of light years away, but a supernova within about 50 light years could spell disaster for Earth. The radiation unleashed would bombard the solar neighborhood with gamma rays and cosmic rays, engaging in a dangerous dance with our planet's atmosphere. In the moments after such an explosion, a fierce gamma ray burst could ravage the ozone layer, the Earth's crucial shield against the sun's harmful ultraviolet radiation. This destruction could linger for months or even years, exposing the surface to intensified UV radiation. Such exposure threatens life itself. DNA damage could skyrocket mutation rates, cancer risks would rise, and entire ecosystems might collapse. One particularly vulnerable group is phytoplankton, the tiny organisms forming the foundation of the ocean's food web. Damage to these microscopic powerhouses would ripple through marine ecosystems, jeopardizing global food resources and the balance of life in Earth's waters. The cosmic assault doesn't stop there. The relentless stream of cosmic rays from a nearby supernova can alter atmospheric chemistry, ionizing nitrogen and oxygen molecules and spawning nitrogen oxides. These compounds act as catalysts for further ozone destruction, deepening the planetary crisis. Beyond the ozone's devastation, these chemical changes could trigger a dramatic cooling of Earth's surface, a phenomenon scientists call an impact winter. This temperature plunge would disrupt weather patterns, stunt agriculture, and push countless species toward extinction if the stress exceeds their ability to adapt. Thus, the radiation from a supernova sets off a chain reaction from the upper atmosphere down to the biosphere, highlighting the fragile interconnectedness of Earth's systems and their vulnerability to cosmic events. These realities underscore the urgent need to study and understand such stellar catastrophes, revealing how intimately our planet's fate is linked to the violent rhythms of our galaxy. Among the universe's most extreme and energetic objects are blazars, blazing beacons of active galactic nuclei that captivate astronomers worldwide. At their core lies a supermassive black hole, millions or billions of times more massive than our Sun, voraciously consuming matter from a surrounding accretion disk. What sets blazars apart is the orientation of their relativistic jets, streams of charged particles accelerated to nearly light speed, directed almost precisely toward Earth. Fueled by the immense gravitational and magnetic forces around the black hole, these jets convert matter into energy with staggering efficiency, lighting up the cosmos like celestial lighthouses visible across billions of light years. Blazars exemplify the universe's power and mystery, where matter, energy, and gravity collide in spectacular displays that challenge our understanding of physics. Their intense emissions not only illuminate the farthest reaches of space, but also shape the environments of their host galaxies, reminding us that the cosmos is a dynamic, ever-changing theater of creation and destruction on a scale beyond human imagination. The energy unleashed by these cosmic jets is nothing short of staggering, stretching across unimaginable distances of the universe and interacting with anything daring to cross their path. Imagine for a moment a blazar jet intersecting with a solar system like ours. What follows could be catastrophic. These jets emit intense high-energy radiation, including X-rays and gamma rays, powerful enough to strip electrons from atoms, creating fiercely ionizing environments in planetary atmospheres. This process could drastically alter the delicate balance that sustains life. The consequences on Earth would be profound. The ionization of the atmosphere would lead to a surge in harmful radiation reaching the surface, devastating living organisms. DNA and cellular structures could suffer severe damage, increasing cancer risks and sparking widespread biological turmoil. Over time, the integrity of our atmosphere itself could be compromised. Energetic particles would trigger complex chemical reactions, threatening to erode the ozone layer that protects all life from the sun's brutal ultraviolet radiation. Furthermore, the planet's magnetic field might be disrupted, crippling satellites, communication networks, and critical technology, throwing civilizations into turmoil. Blazars have been observed to influence regions millions of light years away, a testament to their immense power and potential threat. While Earth remains safe from any known direct hits, understanding these cosmic hazards reminds us of the dynamic and sometimes dangerous universe we inhabit. It also emphasizes the importance of continuous astronomical research to predict, prepare for, and possibly mitigate these high-energy phenomena. Beyond blazar jets, cosmic rays present another formidable challenge, especially for human space exploration. These high-energy particles, originating from sources like supernova, our sun, and distant galaxies, hurtle through space at near-light speeds. Unlike Earth, where our atmosphere and magnetic field provide a protective shield, space offers no refuge. Cosmic rays penetrate spacecraft and spacesuits, bombarding astronauts with relentless radiation. The health implications for astronauts are severe. Ionization caused by cosmic rays can damage tissues and DNA, increasing the risks of cancer, cataracts, and degenerative diseases. Acute radiation sickness, marked by nausea, fatigue, and impaired cognitive function, is also a threat. Heavy ions, with their massive energy and atomic weight, inflict particularly extensive cellular damage. These particles not only jeopardize human health, but also pose significant risks to spacecraft systems. Cosmic rays can corrupt critical electronics, causing malfunctions in navigation, communication, and life support, while degrading materials like solar panels and shortening mission lifespans. To confront these dangers, scientists and engineers are pushing the boundaries of technology, developing advanced shielding materials, radiation-hardened electronics, and exploring artificial magnetic fields to recreate Earth's protective environment. These innovations are vital as humanity sets its sights on longer space missions, from Mars exploration to establishing permanent lunar bases. Safeguarding astronauts and their spacecraft against cosmic radiation is essential for turning our dreams of deep space travel into reality. The universe is a grand theater of extreme and violent phenomena, where staggering power unfolds beyond human imagination. Among the most spectacular are gamma ray bursts, GRBs, supermassive black hole mergers, and hypernovae, each representing cosmic violence at its peak. GRBs are the universe's most intense explosions, emitting torrents of gamma-ray photons that, for brief moments, outshine entire galaxies. Long-duration GRBs arise from massive stars collapsing into black holes, while short bursts originate from merging neutron stars or neutron star black hole pairs. The energy released in mere seconds during a GRB rivals what the sun will emit over its entire 10 billion year lifetime. Should such a jet be aimed at Earth, it could obliterate the ozone layer, expose the surface to lethal ultraviolet rays, and spark global biological crises. Similarly, the merging of supermassive black holes, giants at the centers of colliding galaxies, creates ripples in spacetime known as gravitational waves. These mergers unleash energy equivalent to multiple supernovae combined, momentarily warping the very fabric of the cosmos. Observatories like LIGO and Virgo have recently detected these waves, confirming the phenomenal power of these events. Hypernovae, an even more extreme form of supernova, occur when stars exceeding 30 times the sun's mass collapse. These cosmic cataclysms produce energies that dwarf typical supernovae and are linked to some of the most powerful gamma-ray bursts, amplifying their destructive potential. Each of these events reveals the dynamic and violent essence of our universe, reminding us of the raw forces that shape it across vast distances. As our understanding deepens, we witness both the breathtaking beauty and unfathomable power woven into the cosmos. Take supernovae, for example, colossal explosions marking a star's death. When a massive star exhausts its fuel, its core collapses, triggering an explosion that can briefly outshine whole galaxies. This burst sends out radiation and material that seeds new stars and planetary systems. Yet, if a supernova were to explode within 30 light-years of Earth, its gamma radiation and cosmic rays could devastate the ozone layer, increasing UV radiation at the surface and risking mutations or mass extinctions. Then there's the dramatic cosmic dance of black holes, titanic gravitational forces stretching and compressing matter in a destructive waltz. When two black holes spiral inward and merge, they send gravitational waves rippling through space-time. Although these waves have no direct impact on Earth's biosphere, they reveal the incredible scale and power of the universe's most extreme events, detectable across unimaginable distances. In every corner of the cosmos, extremes of power and violence shape the grand narrative of existence. Through exploration and study, humanity learns not only to marvel at this cosmic spectacle, but to prepare for the challenges it may bring. But the knowledge we gain from observing these cosmic phenomena can completely transform our understanding of the universe. Moreover, if a black hole were to pass close enough to our solar system, its overwhelming gravitational force could wreak havoc on planetary orbits, triggering catastrophic effects that ripple across our celestial neighborhood. Thankfully, such encounters are exceptionally rare within the vast expanse of the Milky Way. Still, studying these colossal cosmic titans deepens our insight into the fundamental laws of physics and the intricate fabric of cosmology, revealing just how delicate and interconnected our existence is in this immense cosmic ballet. Rogue planets, often called interstellar or nomad planets, are among the universe's most enigmatic wanderers. These solitary worlds drift through space without the warmth or light of a parent star to anchor them. Scientists believe many of these orphan planets were violently ejected from their original solar systems through gravitational tussles, now embarking on lonely voyages across the galaxy. Astoundingly, estimates suggest that for every star in the Milky Way, there could be at least 2 rogue planets, indicating these wandering worlds are far more common than once imagined. Despite the cold, dark void they traverse, some of these planets may still harbor internal heat, fueled by radioactive decay or geological activity deep within, creating rare pockets where life, at least in theory, might survive. Should a rogue planet ever venture close to our solar system, the consequences could be profound. Its immense gravity could disturb the fragile balance that holds our cosmic neighborhood intact. Depending on its size and path, such a planet might disrupt the orbits of comets residing in the distant Oort cloud or the Kuiper belt, sending a flurry of icy bodies hurtling inward toward the sun and the inner planets. This could unleash a barrage of impacts reminiscent of the colossal collision believed to have caused the extinction of the dinosaurs some 65 million years ago. On an even grander scale, if a rogue planet came near enough to the major planets, it might alter their orbits, triggering dramatic climatic shifts on Earth and threatening the stable conditions that have allowed life to thrive. While the chances of such a close encounter remain slim, the possibility itself is a stark reminder of the ever-shifting and sometimes perilous nature of our cosmic environment. Similarly, the threat of a rogue asteroid hurtling toward Earth without warning captures both the imagination of the public and the vigilance of scientists worldwide. Near-Earth objects, NEOs, are tracked rigorously by astronomers who scan the skies with advanced telescopes on the ground and in space. Although most asteroids larger than about 1 kilometer, capable of causing global devastation, have been discovered and monitored, smaller asteroids ranging from a few meters to several hundred meters pose a more subtle but still significant risk. The likelihood of a small rogue asteroid slipping past our detection and striking Earth is low, but cannot be dismissed entirely. Thanks to rapid advances in astronomy, our ability to spot such cosmic interlopers has improved dramatically. Yet the vastness of space and the inherent limitations of our technology leave a veil of unpredictability. For instance, objects approaching from the direction of the sun are especially difficult to detect, as the sun's glare blinds our instruments. To counter this, new technological efforts like NASA's Near-Earth Object Surveillance Mission, NEOSM, and the European Space Agency's FlyEye telescope are being developed to enhance our early warning systems. Despite these cutting-edge initiatives, the sudden appearance of an asteroid remains a sobering reminder of Earth's vulnerability in this vast and dynamic universe. Consequently, international space agencies are also investing in mitigation strategies, including pioneering deflection technologies. Concepts such as using spacecraft to alter the trajectory of threatening asteroids are actively being researched and tested, preparing humanity for a future where we might need to protect our planet from these celestial hazards. This unfolding story of cosmic threats and scientific vigilance illustrates the fragile balance of life on Earth and the profound interconnectedness of our place in the universe. It is a testament to human curiosity and resilience that we continue to study, prepare for, and adapt to the challenges posed by the universe's mysterious wanderers and titanic forces. But imagine the catastrophic ripple effect unleashed by a rogue star drifting into our cosmic neighborhood, a scenario that, while incredibly rare, holds the potential to reshape the very fabric of our solar system. These rogue stars, often called interstellar wanderers, journey through the void untethered, carrying gravitational forces powerful enough to disrupt the delicate balance that has governed planetary orbits for billions of years. Should one of these stellar nomads venture close enough, the gravitational chaos it could unleash would not only distort the orbits of planets, but also send shockwaves through the countless icy bodies residing in the distant Kuiper Belt and the vast Oort cloud. This disturbance could fling asteroids and comets from their usual paths, sending them careening toward the inner solar system, a cosmic rainstorm of potential destruction. The increased frequency of collisions would pose an existential threat to Earth, reminiscent of the massive impact events that have shaped life's history, triggering mass extinctions and radical shifts in climate. Over prolonged periods, the gravitational tug from a rogue star might even alter planetary orbits so drastically that Earth could be pushed into a climate-altering trajectory, threatening the stability required for life as we know it. Yet the universe holds threats even more enigmatic and elusive. Rogue black holes, remnants of colossal stars that have collapsed into points of infinite density, drift silently across the galaxy. Invisible to the naked eye, these cosmic phantoms reveal themselves only through the havoc their immense gravity wreaks on surrounding matter. A wandering black hole passing near our solar system could unleash forces capable of warping the orbits of planets, flinging them into the abyss of interstellar space, or pulling them into fatal spirals. Even without direct contact, the gravitational perturbations could destabilize asteroid belts, hurling a deadly hail of debris inward. The tidal forces might stretch and compress planetary bodies, sparking volcanic eruptions, tectonic upheavals, and geological chaos. While such an encounter is extraordinarily unlikely, the mere possibility serves as a haunting reminder of the precariousness of our cosmic home. Advances in astronomy, particularly in detecting gravitational waves and monitoring stellar movements, strive to uncover these hidden threats before they approach too near. And then there are rogue planets. massive, untethered celestial bodies wandering the galaxy alone. Should such a planet, perhaps rivaling Jupiter or Saturn in size, drift into our solar system, its gravitational influence could unsettle the orbits of distant gas giants like Neptune and Uranus. This cascading effect could ripple inward, warping Earth's orbit and triggering extreme climate shifts, from unrelenting heat waves to icy freezes, disrupting ecosystems and agriculture worldwide. The disturbance could also send asteroids and comets inward, amplifying the risk of catastrophic impacts reminiscent of the event that wiped out the dinosaurs. A close encounter between a rogue planet and a gas giant might even eject planets from the solar system, destabilizing the entire celestial dance that has endured for eons. Far beyond the planets lies the Oort cloud, a spherical shell of icy objects marking the solar system's edge. This reservoir of comets, millions of miles distant, is susceptible to nudges from passing stars, galactic tides, or hypothetical massive bodies like the mysterious Planet 9. When these icy wanderers are disturbed, they embark on lengthy voyages toward the sun, sometimes crossing Earth's path at terrifying speeds. Unlike the relatively stable asteroids in the inner solar system, these comets can be enormous and fast. Their icy nuclei glowing spectacularly as solar heat causes their ices to vaporize, creating brilliant comas and tails visible across the night sky. In this vast cosmic arena, the fragile harmony of orbits, gravities, and trajectories reminds us how even the most remote or seemingly insignificant interstellar encounters carry the power to influence life on our pale blue dot. While these celestial dramas unfold on scales and timelines far beyond human experience, they underscore the awe-inspiring dynamic nature of the universe and the extraordinary fortune we enjoy in the calm of our solar system's present day. But also increasing their fragmentation potential means that a single comet, once thought to be a solitary cosmic wanderer, can shatter into multiple smaller fragments, each one still deadly, each one a formidable threat hurtling through space. Imagine a rogue comet breaking apart as it barrels toward Earth, its shattered pieces spreading devastation across the globe. Such a scenario is not merely the stuff of science fiction. It echoes the catastrophic event known as the Chicxulub impact, a cosmic collision 65 million years ago that reshaped life on Earth and led to the extinction of the dinosaurs. The terrifying reality is that a similar encounter today could unleash consequences far beyond our worst fears. The challenge we face is monumental. Detecting these rogue comets early enough to track their unpredictable trajectories and devise strategies to deflect or mitigate their impact. Unlike near-Earth asteroids that often follow more predictable paths, these icy nomads arrive from the farthest reaches of the solar system or even beyond, with highly eccentric orbits that can swing wildly through the cosmic neighborhood. Their erratic journeys render them elusive targets, slipping past conventional detection methods. Yet, our technological arsenal is growing stronger. Advanced wide-field survey telescopes, both ground-based and spaceborne, are scanning the skies with unprecedented sensitivity, allowing us to spot these icy threats sooner. Missions like the European Space Agency's Rosetta, which studied Comet 67P up close, provide invaluable data about comet composition and behavior, knowledge essential for crafting future defense mechanisms. Meanwhile, the prospect of a rogue neutron star passing near Earth elevates the stakes to an almost unimaginable level. These remnants of massive stars, compressed into spheres barely 20 kilometers wide, yet containing masses comparable to our Sun, possess gravitational forces so intense they warp space and time itself. A rogue neutron star's close approach could unleash havoc in our solar system. Planets thrown into erratic orbits, some potentially ejected into the void, moons torn from their paths, and Earth itself subjected to extreme gravitational stresses. Such forces could trigger massive earthquakes, volcanic eruptions, and tsunamis, nature's fury magnified to apocalyptic scales. The disruption could alter Earth's orbit if plunging the planet into a hostile climate inhospitable to the life we know. Adding to the danger, neutron stars often emit intense beams of radiation, X-rays and gamma rays, from their magnetic poles. If Earth were caught in this deadly radiation, our atmosphere could be stripped away, exposing every living creature to lethal doses of radiation. Unlike black holes, whose menace lies primarily in their gravity and invisibility, Neutron stars combine gravitational disruption with devastating radiation emissions, creating a dual threat of cosmic proportions. Thankfully, the probability of such a catastrophic encounter remains extraordinarily low, given the immense distances between neutron stars and our solar system, and their relative scarcity in our galactic neighborhood. But the mere possibility highlights the raw power and unpredictable nature of our universe. Continuous astronomical observation and in-depth study of neutron stars and other stellar remnants are essential if humanity hopes to one day predict and perhaps prevent the devastating effects of these cosmic interlopers. Rogue celestial objects, whether planets, stars, or even black holes, often travel through the vastness of space unnoticed, their presence masked by darkness and distance. Many lack intrinsic luminosity. Unlike the stars that shine brightly, they emit little to no light of their own. Rogue planets drifting far from any star reflect only faint starlight, making them ghosts against the cosmic backdrop. Black holes, by their very nature, are invisible, detectable only through their gravitational influence on nearby matter or the high-energy X-rays produced as they consume material. The immense scale of the universe compounds the difficulty. Space is a crowded canvas filled with stars, galaxies, and nebulae, all emitting light that overwhelms the faint signatures of these elusive objects. Detecting a solitary, dark wanderer in this cosmic haystack demands cutting-edge technology. Ground-based and spaceborne telescopes, equipped with advanced detectors and wide-field cameras, tirelessly scan the heavens, focusing on specific regions to unveil hidden threats. Each discovery, each observation, brings us closer to understanding the rogue elements of our universe and equips humanity with the knowledge to face potential cosmic catastrophes head-on. As we continue to push the boundaries of astronomical science, we strengthen Earth's shield against the unknown, proving that vigilance and innovation are our greatest defenses against the unpredictable dangers lurking in the depths of space. But they can still miss rogue objects unless they are purposefully searching for subtle gravitational anomalies or indirect signs of their presence. The universe holds countless secrets, and these wandering celestial bodies slip through our cosmic nets, hidden from even the most advanced technological eyes. Despite the incredible power of today's telescopes, limitations in resolution and sensitivity mean faint objects, especially those that do not emit their own light, often go undetected. Our quest to find these rogue objects often depends on watching for the ripple effects they create. Gravitational lensing, where the immense gravity of a massive object bends and warps the light from distant stars, or erratic movements of stars and other bodies influenced by an invisible cosmic wanderer nearby. Initiatives like the upcoming Vera C. Rubin Observatory, designed to repeatedly survey the entire sky, represent humanity's boldest effort yet to unveil these elusive travelers. By scanning vast stretches of space multiple times, it increases the chances of spotting these dark, drifting nomads. Complementing this, enhanced detection techniques using infrared and radio waves are crucial, revealing faint traces of rogue objects silently traversing the interstellar void. Each new detection peels back a layer of mystery, revealing a universe far more dynamic and unpredictable than previously imagined. The implications of a rogue black hole consuming planets in its path are both awe-inspiring and terrifying, challenging our understanding of cosmic events and revealing dangers lurking in the vastness of space. A black hole's defining power is its immense gravitational pull, capable of capturing anything that ventures too close, even entire planets. Unlike black holes anchored in galaxies or stellar systems, a rogue black hole drifts freely through the cosmic ocean, acting as a relentless vacuum cleaner, swallowing planets, asteroids, and any matter caught in its trajectory. When such a black hole encounters a planet, the forces unleashed are catastrophic. The planet undergoes spaghettification, a chilling process where it is stretched and compressed by extreme tidal forces. Imagine a planet stretched like taffy along the axis facing the black hole, compressed perpendicular to that axis until it ultimately tears apart. As the planet's debris spirals inward, it forms a searing accretion disk, radiating immense energy before crossing the event horizon, the point of no return, beyond which nothing escapes. This violent cosmic dance has profound consequences. The sudden loss of a planet can destabilize neighboring orbits, setting off a chain reaction of gravitational chaos throughout the system. Such disturbances might cause planets to collide or be hurled into deep space, increasing the disorder within the stellar neighborhood. Moreover, the brilliant radiation from the accretion disk serves as a rare cosmic beacon, allowing astronomers to detect and study these otherwise invisible black holes, unlocking insights into the extreme physics that govern their existence. Speculating even further, if a rogue black hole were to enter our own solar system and consume a planet, be it mighty Jupiter or smaller worlds, the aftermath would be catastrophic. The gravitational turmoil alone could render the solar system unrecognizable, disrupting the delicate orbital ballet of planets, triggering collisions or sending planets spiraling into the dark void between stars. For Earth, this could mean environmental upheavals incompatible with life or total annihilation. While the likelihood of such an event is astronomically low, it underscores the rare yet existential risks roaming the universe, compelling us to remain vigilant and push the boundaries of cosmic knowledge. Rogue objects, whether wandering planets, stars, or black holes, bring chaos to established star systems. Their gravitational influence can shake the harmonious orbits of planets, moons, asteroids, and comets, often with catastrophic consequences. Even small perturbations can cascade, causing drastic shifts in orbital dynamics. Picture a rogue planet drifting into a star system and nudging planets into collision courses, ejecting them into space, or sending them plunging into their host star. Such disruptions not only threaten the stability of those planets, but also can trigger severe climate changes, potentially extinguishing life. The effect extends to smaller celestial bodies. Altered orbits of asteroids and comets may send waves of these objects crashing into inner regions of star systems, increasing impact events that reshape planetary surfaces and influence the course of evolution. Our own solar system's history may bear witness to such disturbances. Some scientists suggest interactions between Jupiter and Saturn in the distant past, scattered comets from the Kuiper Belt, influencing impact rates on Earth and possibly shaping the emergence of life. When a rogue star or black hole enters the scene, the stakes become even higher. Their colossal gravitational fields can disrupt entire star systems, inducing chaos on a massive scale. In extreme cases, a rogue black hole's tidal forces can tear apart planets and stars, a dramatic event known as tidal disruption. The resulting debris forms a glowing accretion disk, emitting intense radiation that not only wreaks havoc locally, but broadcasts a cosmic signal to distant observers. These phenomena remind us that our universe is a dynamic, ever-changing arena where order and chaos constantly wrestle. The silent passage of rogue objects challenges our understanding and fuels our curiosity, beckoning astronomers and physicists to unlock the mysteries of these cosmic nomads. Through relentless observation and advancing technology, we inch closer to unveiling their secrets, deepening our grasp of the universe's true nature and our fragile place within it. But could also be detected across the vast expanse of the galaxy, serving as a stark and chilling reminder of the immense destructive potential lurking within rogue objects. These cosmic nomads, unbound by the gravitational ties of any star, pose a significant threat to the delicate balance and stability of established star systems. Their immense gravitational influence can unleash a cascade of chaos, from disrupting planetary orbits to hurling planets into the void, from triggering catastrophic collisions to unleashing intense bursts of radiation. These disturbances fundamentally transform the intricate dynamics of affected systems, turning once habitable worlds into barren wastelands, inhospitable to any form of life as we know it. The rarity of such rogue encounters only amplifies their dramatic nature, underscoring the critical importance of relentless astronomical surveillance and dedicated research. In tracking these formidable cosmic wanderers, scientists aim to deepen humanity's understanding of these mysterious threats that roam the dark corners of our universe. The universe itself is a sprawling, enigmatic expanse, an endless canvas painted with mysteries that continue to confound even the most brilliant scientific minds. Despite remarkable strides in cosmology, one of the universe's most unsettling secrets remains the elusive nature of dark matter and dark energy. Together, these invisible forces constitute roughly 95% of the total mass energy content of the cosmos. Dark matter, an elusive form of matter, neither emits nor absorbs light, rendering it completely invisible. It reveals itself only through the subtle gravitational effects it exerts on galaxies and galaxy clusters, shaping the very scaffolding of the cosmos. Even more mysterious is dark energy, a pervasive, unseen force accelerating the universe's expansion at a rate that defies our conventional understanding of physics. Numerous theories and experiments have sought to uncover their true nature, yet their origins and fundamental properties continue to evade our grasp, leaving us with a haunting realization. The vast majority of our universe is composed of something utterly unknown. Adding to this cosmic puzzle is the enigmatic nature of black holes, especially the supermassive giants anchoring the hearts of galaxies, including our own Milky Way. While Einstein's theory of general relativity provides profound insights into many features of black holes, their event horizons and singularities, what unfolds beyond these thresholds remains cloaked in mystery. Singularities, points where density becomes infinite and the known laws of physics collapse, challenge our most fundamental understanding of space-time. The infamous information paradox, questioning the fate of information swallowed by a black hole, adds further complexity, hinting at unresolved tensions between quantum mechanics and general relativity. These enigmas drive physicists to the frontier of theoretical science, pushing them to reconcile the universe's grandest scales with its smallest building blocks. Meanwhile, questions about the universe's origin and its ultimate destiny continue to perplex cosmologists. The Big Bang theory stands as a powerful framework for the birth of the cosmos, yet it leaves open profound mysteries. What, if anything, preceded the Big Bang? Does the very concept of before even hold meaning in the fabric of time and space? Similarly, the universe's fate is shrouded in speculation, with competing scenarios, be it a cataclysmic big crunch, an endless big freeze, or a violent big rip, each painting a future so alien and incomprehensible it strains the limits of human imagination. Beyond these, even deeper questions arise about the true nature of time, the tantalizing possibility of multiple universes or hidden dimensions, and the potential existence of extraterrestrial life. These cosmic unknowns frame a daunting yet inspiring frontier, urging humanity to probe ever deeper into the mysteries that define our existence. The universe is not only vast, but also dynamic and unpredictable. Among the sudden and devastating cosmic events that could imperil life on Earth, gamma-ray bursts, GRBs, rank as some of the most powerful and feared. These extraordinary explosions unleash staggering amounts of energy in mere seconds, often resulting from the catastrophic collapse of massive stars or the violent merger of neutron stars. Should a gamma-ray burst occur within our own galaxy, its consequences for Earth could be catastrophic, bathing the planet in lethal radiation that disrupts our atmosphere and threatens all forms of life. These cosmic cataclysms remind us of the precariousness of our place in the cosmos, reinforcing the vital need for vigilance, scientific inquiry, and preparedness as we continue to navigate the mysteries and marvels of the universe. But several thousand light years away, a cosmic event could still cast a shadow over Earth in ways that challenge our very survival. The intense gamma radiation unleashed by such an explosion has the terrifying potential to strip away our planet's ozone layer, a delicate shield that guards all life from the sun's harmful ultraviolet rays. Without this protective barrier, an immediate surge in UV radiation would batter the surface, igniting a spike in skin cancers, wreaking havoc on plant life and unraveling entire food chains. This chain reaction could cascade into mass extinctions, a chilling reminder of our planet's fragility in the face of cosmic forces. And yet, this is only part of the story. Imagine a supernova explosion occurring within 25 light years, a relatively close neighbor by cosmic standards. While no nearby stars are expected to explode soon, such a supernova would release a torrent of gamma and X-rays, but also a flood of high-energy cosmic rays. These invisible projectiles would bombard Earth's atmosphere, further degrading the ozone layer and allowing lethal UV radiation to pour in. The aftermath could plunge our planet into a cosmic winter, as debris and dust from the explosion obscure sunlight. This sudden cooling would devastate global agriculture, triggering food shortages and ecological collapse on an unprecedented scale. Yet another looming threat lies in the silent approach of rogue asteroids or comets. Despite extensive detection programs that have cataloged many near-Earth objects, smaller, elusive travelers still evade our gaze. If one were to collide with Earth, the impact could unleash tsunamis, wildfires, and send vast amounts of particulate matter into the stratosphere, blocking sunlight for months or even years. This impact winter would chill the globe, plunging ecosystems into chaos and threatening the survival of countless species, including our own. In every one of these cosmic catastrophes, unpredictability reigns supreme. Our current technological limits in detection and prevention underscore Earth's vulnerability amid the vast, uncharted expanse of space. Continuous advancement in our observational tools is not merely an academic pursuit, but a race for survival, equipping us with the means to anticipate threats and develop strategies to safeguard life on our fragile planet. But the dangers are not always from distant stars or celestial objects. Humanity itself may unwittingly trigger cosmic catastrophes. Consider the experiments at facilities like the Large Hadron Collider, LHC, where particles are smashed together at nearly the speed of light to mimic conditions just after the Big Bang. Some speculative theories suggest these collisions might create microscopic black holes. Though scientists widely agree these would evaporate almost instantly through Hawking radiation, the shadow of uncertainty lingers. The unknown behavior of these phenomena raises questions about what unforeseen consequences might arise from pushing nature's limits. Moreover, theoretical physicists discuss the possibility of vacuum decay, an event where our universe, currently trapped in a false vacuum, could transition to a lower energy true vacuum. Such a shift could create a bubble expanding at the speed of light, obliterating everything in its path. While this terrifying scenario remains deeply speculative, and the energies in human experiments are far too low to provoke it, the concept challenges our understanding of the universe's stability and our place within it. In the end, these stories, woven from the threads of astrophysics, quantum mechanics, and cosmic mystery, remind us of both the awe-inspiring power of the universe and our profound vulnerability. As we look up at the stars, we must also look inward at our own advances, mindful that the cosmos can be both a cradle and a crucible for life. Vigilance, curiosity, and humility will be our greatest allies in navigating the dangers that lurk just beyond the veil of our sky. But the sheer vastness of the cosmos reminds us of how little humanity truly comprehends about the fundamental fabric of our universe. As our technology advances at an unprecedented pace, so too does our capacity to influence and potentially interfere with celestial bodies. Cutting-edge space missions now contemplate daring ventures like mining asteroids for precious resources or nudging their orbits to steer them away from catastrophic collisions with Earth. Yet, these ambitions carry profound risks. A simple miscalculation, an unforeseen reaction, or an unexpected gravitational interplay could inadvertently set an asteroid on a collision course with our planet rather than away from it. Similarly, envisioning the future where we tap into cosmic energy reservoirs or manipulate the behavior of stars presents theoretical yet chilling possibilities. Extreme scenarios, still firmly in the realm of speculation, imagine destabilizing the delicate gravitational and energetic balances that hold galaxies and solar systems in harmony. Such outcomes underscore a vital truth: with great power over the cosmos comes an equally great responsibility. Our growing understanding of cosmic forces must be matched by ethical foresight and caution. Engaging the global scientific community in open dialogue and establishing rigorous safety protocols are not just advisable, they are imperative. Only through international collaboration and stringent oversight can we hope to prevent the unintended unleashing of catastrophic consequences that could reverberate through space and time. The unpredictable nature of cosmic phenomena constantly keeps scientists vigilant. The universe's scale and complexity are staggering. Billions of galaxies, each harboring billions of stars and an uncountable multitude of planets. Within this immense canvas, potential cosmic events abound, from supernova and gamma-ray bursts to rogue planets wandering through the void and enigmatic black holes consuming light itself. Even armed with the most advanced telescopes and sophisticated theoretical models, accurately predicting when or where these dramatic events might strike remains a monumental challenge. Compounding this uncertainty is our incomplete grasp of many astrophysical processes. We understand the mechanics of supernova explosions in principle, but the subtle precursors to these colossal detonations often evade detection from Earth-based observatories. Gamma-ray bursts, those brief yet extraordinarily powerful flashes of energy, appear and vanish in mere seconds, often leaving behind little trace. Should one occur near Earth, the consequences for life as we know it could be devastating, potentially altering our planet's biosphere in ways we are only beginning to fathom. The rarity of such events belies their catastrophic potential. Even a minor uptick in the probability of a nearby gamma-ray burst or supernova could have far-reaching implications for planetary safety and cosmic risk assessment. Delving deeper into the cosmic unknowns, the search for dark matter and dark energy, the elusive substances comprising approximately 95% of the universe's total mass energy content, exemplifies the challenges and mysteries that continue to baffle astronomers and physicists. Despite decades of research, these invisible forces defy direct detection and confound existing models. Observational data often challenges long-held theories, pushing the scientific community to consider bold and sometimes contradictory new ideas, each step further unfolding the cosmic enigma. Meanwhile, nearer to home, the dynamic and often chaotic movements of asteroids and comets add yet another layer of unpredictability. Near-Earth objects, NEOs, constantly shift their trajectories, influenced by gravitational tugs from planets and subtle forces like the Yarkovsky effect, a phenomenon where solar radiation absorbed and then re-emitted by a small body causes a gradual but significant change in its orbit. These small shifts can make it incredibly difficult to track these objects with precision, sometimes leading to late discoveries of potential impact threats. This delicate dance of cosmic forces, this interplay of knowns and unknowns, places humanity in a unique position. We are explorers and innovators, driven by curiosity and ambition, yet we tread on a cosmic stage filled with hidden dangers and profound mysteries. Our ongoing journey to understand and interact with the universe demands humility, vigilance, and a commitment to stewardship, not only of our own planet, but of the vast cosmic environment that surrounds us. The unpredictable and often violent nature of cosmic events challenges our understanding of the universe at every turn. Because of this, astronomers, astrophysicists, and planetary scientists must remain constantly vigilant, pushing the boundaries of knowledge by regularly updating their models, refining observational techniques, and forging international collaborations. These global efforts are vital, not only to safeguard our planet from cosmic threats that emerge without warning, but also to unravel the universe's most profound mysteries. One of the most baffling phenomena observed in space is the enigmatic fast radio bursts, or FRBs. First detected in 2007, these fleeting signals last only a few milliseconds, yet unleash in that brief instant more energy than our sun emits in an entire day. For years, the source of these bursts remained elusive, a cosmic riddle. It wasn't until astronomers traced one of these bursts back to a galaxy over 3 billion light-years away that a faint thread of understanding emerged. But even with many detections since, the origin of FRBs remains fiercely debated. Some scientists suggest they are produced by highly magnetized neutron stars, celestial bodies with magnetic fields billions of times stronger than Earth's. Others have even speculated that these bursts might be signs of advanced alien technology sending signals across the cosmos. The mystery deepened further when astronomers discovered repeating FRBs, contradicting earlier assumptions that they were one-time cosmic flashes and adding intricate layers to this celestial puzzle. Equally compelling is the phenomenon of dark matter and dark energy, which together compose about 85% of the total mass and energy in the universe, yet remain invisible and undetectable by direct means. Their presence is inferred solely through the gravitational effects they exert on galaxies and galaxy clusters. Dark matter acts as an invisible framework, an unseen scaffolding that holds galaxies together despite their rapid rotation, all while refusing to emit, absorb, or reflect any light. Dark energy is an even more profound mystery. It is believed to be driving the accelerated expansion of the universe, a revelation that earned the Nobel Prize in Physics in 2011. Yet, the true nature of dark energy remains one of the most pressing and tantalizing questions in cosmology today. challenging our very understanding of physics and the fabric of reality. Closer to home, our own star, the Sun, can unleash sudden and intense bursts of activity with far-reaching consequences for Earth. Solar flares, massive explosions of energy caused by the sudden rearrangement of magnetic fields on the Sun's surface, can sometimes trigger coronal mass ejections, CMEs. These gigantic expulsions of plasma and magnetic fields travel across space, and if they collide with Earth's magnetosphere, can cause severe disruptions. History offers a sobering example: the Carrington event of 1859, a massive geomagnetic storm that knocked out telegraph systems across Europe and North America. If a similar event struck today, it could cripple our modern technological infrastructure, disabling electrical grids, satellites, and communication networks, plunging cities into darkness and isolating millions. Beyond the immediate technological havoc, increased solar activity can also impact Earth's climate and atmosphere. High-energy particles emitted by solar storms can damage the ozone layer, our planet's crucial shield against harmful ultraviolet radiation. A compromised ozone layer means more UV rays reach the Earth's surface, elevating the risks of skin cancer and other serious health problems for all living beings. As our civilization grows ever more dependent on technology, and as we peer deeper into space, understanding and preparing for these cosmic forces becomes not just a scientific pursuit, but a necessity for the survival and flourishing of life on Earth. Moreover, increased solar radiation doesn't just brighten our days, it has the power to reshape our planet's very climate and weather patterns, sometimes with devastating consequences. The warmth and light we receive from the sun are vital for life, but a sudden, intense surge in solar activity could unleash a cascade of catastrophic events on Earth. This is why scientists and governments worldwide invest heavily in sophisticated monitoring systems and preparedness strategies to face the challenges of space weather head-on. Solar flares and coronal mass ejections, or CMEs, are at the heart of these cosmic threats. Solar flares are sudden, intense bursts of radiation caused by the explosive release of magnetic energy from the sun's surface. When these flares erupt, they send waves of high-energy radiation hurtling through space, directly impacting Earth's ionosphere, the upper layer of our atmosphere charged with ions and electrons. The result? Disruptions in high-frequency radio communications, which are essential for everything from airline navigation to maritime operations and military command. Imagine a world where airplanes lose communication mid-flight, or naval vessels cannot coordinate. These aren't distant sci-fi scenarios, but real risks during solar flare events. Yet the danger doesn't stop there. CMEs are even more formidable, gigantic clouds of charged solar particles ejected at speeds reaching millions of miles per hour. When a CME collides with Earth's magnetic field, it can trigger geomagnetic storms that ripple through our power grids, pipelines, and communication networks. These storms induce powerful electric currents that can overload transformers and fry critical infrastructure. The consequences? Widespread blackouts, potentially plunging entire cities or even countries into darkness for days or weeks. The chaos of such outages would disrupt everything, from hospitals relying on electrical equipment to everyday household activities, highlighting our modern world's vulnerability to celestial tempests. Space-based assets face similar threats. Satellites orbiting Earth form the backbone of modern life, enabling global communications, GPS navigation, weather forecasting, and financial transactions. However, the intense radiation and charged particles from solar flares and CMEs can damage or disable these satellites, knocking out services we often take for granted. For astronauts aboard the International Space Station or future deep space missions, exposure to increased radiation levels can be life-threatening, causing acute radiation sickness, increasing cancer risks, and damaging internal organs. Thus, space weather is far from a distant astronomical curiosity. It is an immediate, tangible hazard with direct implications for humanity's technological and exploratory future. Beyond solar phenomena, the universe presents other potential threats lurking quietly on the edges of our solar system. Rogue planets or interstellar comets, wandering celestial objects not bound to any star, drift through our galaxy, occasionally venturing close enough to disturb the delicate gravitational harmony of our solar neighborhood. Should such a wandering body pass near, Its gravitational pull could disrupt the orbits of planets, asteroids, or comets. Even a slight perturbation of a large asteroid in the asteroid belt might send it careening toward Earth, triggering catastrophic impacts. Moreover, these interstellar wanderers might interact with the Oort cloud, a vast, icy shell encasing the solar system's outermost boundaries. This interaction could fling a shower of comets toward the inner solar system, significantly increasing the risk of devastating impacts. Scientists speculate that a comet or asteroid impact of this nature caused the mass extinction event that wiped out the dinosaurs some 65 million years ago, forever altering Earth's biological trajectory. Such encounters could also result in prolonged meteor showers, posing persistent risks of destructive impacts that could affect not only Earth, but other planets as well. While such scenarios remain rare, their potential consequences demand constant vigilance. Advanced astronomical observatories and monitoring programs scan the skies daily to detect and track these wandering objects well before they pose a threat. Early detection is crucial, providing valuable time to develop and deploy deflection strategies or other defensive measures, steps that could mean the difference between disaster and survival. Finally, consider the immense stakes if a massive asteroid were discovered on a collision course with Earth. The impact of a space rock, just a few kilometers across, would unleash energy equivalent to millions of nuclear bombs detonating simultaneously. The aftermath would be catastrophic, massive earthquakes shaking the planet's crust, tsunamis surging across oceans, and a powerful shockwave obliterating all life in the immediate vicinity. The collision would hurl enormous quantities of dust and debris high into the atmosphere, blocking sunlight and plunging the planet into a prolonged impact winter. This darkness would disrupt photosynthesis, and this is collapse ecosystems and threaten global food supplies, ushering in a period of severe climate upheaval. In this way, the universe reminds us that Earth's tranquility is fragile, perched precariously amidst cosmic forces both seen and unseen. Our survival depends not only on understanding these forces, but on building resilience through vigilant observation, scientific innovation, and global cooperation. As we gaze toward the stars, we must remember that while the cosmos holds beauty and mystery, it also demands respect and preparedness, lest we be caught unawares by the celestial storms on the horizon. This could drastically reduce temperatures worldwide, collapse ecosystems, jeopardize food production, and result in mass extinctions reminiscent of the cataclysmic event that wiped out the dinosaurs some 65 million years ago. Imagine the chilling silence that would follow such devastation. Entire species erased, delicate balances shattered, and a world forever altered. And yet, this looming threat is not the stuff of distant history or science fiction. It is a very real possibility that underscores the fragile position of life on Earth. Our current asteroid detection systems, while impressively advanced, are not foolproof. Smaller asteroids, or those hurtling towards us from the sun's blinding direction, could slip past undetected, leaving us with precious little time to respond. The window to act is painfully narrow, and any effective countermeasure demands rapid coordination, immense preparation, and cutting-edge technology. Potential strategies to deflect or destroy an incoming asteroid span a range of daring concepts, from the explosive power of nuclear detonations aimed at nudging it off course, to kinetic impactors designed to alter its trajectory with a precise collision, to the futuristic idea of gravitational tractors, spacecraft that use their own gravity to gently pull an asteroid onto a safer path. But all of these depend on the early warning that our current systems sometimes cannot guarantee, making the continuous investment in asteroid detection technologies not just prudent, but imperative. As our planet's defenses grow, the ominous possibility of an unseen celestial threat continues to haunt our scientific imagination, a stark reminder that amid the vast cosmic arena, Earth remains vulnerable. And this vulnerability extends beyond asteroids to the growing problem of space debris, or space junk, which threatens both our orbital infrastructure and terrestrial operations. The space surrounding Earth is cluttered with defunct satellites, spent rocket stages, fragments from collisions and explosions, and even tiny flecks of paint that travel at mind-boggling speeds of up to 17,000 miles per hour. At such velocities, even the smallest piece of debris can inflict severe damage. A collision with a particle no larger than a millimeter can pierce the hull of a spacecraft, while larger fragments could obliterate satellites worth hundreds of millions of dollars or endanger astronauts aboard the International Space Station. Among the gravest concerns is the potential for a catastrophic chain reaction known as the Kessler syndrome, first proposed by NASA scientist Donald J. Kessler in 1978. This scenario envisions a cascade of collisions, each one generating an exponentially growing cloud of debris that increases the odds of further impacts in a deadly feedback loop. If triggered, the Kessler syndrome could render entire orbital regions perilous, halting satellite launches, crippling communications, and stalling humanity's aspirations for space exploration. Moreover, some of this debris could eventually re-enter Earth's atmosphere unpredictably, posing threats to populated areas. Tackling this invisible menace demands unprecedented international collaboration and technological innovation. Continuous tracking and cataloging of debris, pioneering methods to safely deorbit retired satellites, and advanced shielding for spacecraft to withstand high-speed impacts. Researchers are also pioneering groundbreaking solutions such as laser-based debris removal systems and robotic space janitors designed to sweep orbit clean. Yet, with the relentless rise in space traffic and the proliferation of satellites, the challenge of preserving safe orbital pathways is only intensifying, making the safeguarding of our cosmic neighborhood a critical priority for the future of both space and life on Earth. And beyond these tangible dangers, the theoretical existence of advanced alien civilizations introduces profound and enigmatic possibilities. The Great Filter Hypothesis, a chilling concept in the search for extraterrestrial intelligence, suggests that civilizations inevitably encounter an existential barrier, a filter, that either halts their progress through self-destruction or propels them into an unknown state of advanced existence. If such civilizations exist and have successfully navigated this filter, encountering them could reveal insights into survival or pose unimaginable threats. The unknown nature of these potential encounters invites both hope and caution, as humanity stands at the dawn of an era where the cosmos is not merely a vast emptiness, but a realm teeming with mysteries yet to be unraveled. The stakes are immense, from cosmic catastrophes and orbital dangers to the very question of our place in the universe. These challenges compel us to forge ahead with vigilance, ingenuity, and a collective will to protect our fragile world. But the question remains, if extraterrestrial beings truly exist and observe us, would their intentions be benign, or could they harbor hostility toward humanity? This is not mere speculation. It's a profound inquiry into the fate of our species in a cosmos that might hold civilizations far older and more advanced than ours. Should these beings perceive humanity as a threat, or worse, as expendable, the consequences could be catastrophic. From technological disruption that dismantles our current way of life to outright annihilation, the stakes could not be higher. Consider the possibility that such an advanced civilization possesses technologies so far beyond our grasp that they might appear as magic to us, echoing Clarke's third law. Any sufficiently advanced technology is indistinguishable from magic. Imagine entities capable of bending space-time, engineering entire planets, or harvesting energy directly from stars. Their power might render humanity almost insignificant on the cosmic stage. An accidental encounter could expose us to manipulation on levels we can scarcely comprehend. Mind control, enslavement through AI or biotechnology, or ecological devastation via engineered pathogens and deliberate climate manipulation. The sheer scale of such capabilities is daunting. Moreover, the detection or contact with such beings would ripple through every corner of our world. The shock alone could trigger global panic, shaking the foundations of our political systems, economies, and deeply held beliefs. Philosophically, humanity would face an existential crossroads. Our view of ourselves, our place in the universe, and the meaning of life itself could be transformed overnight. This shift might unite humanity in ways never before seen, or conversely, it could fracture societies as different cultures and ideologies struggle to make sense of the new reality. This is why many theorists advocate for caution. Some urge careful, deliberate approaches in any interaction with advanced extraterrestrial life, emphasizing the risks of indiscriminate broadcasting of our presence. Others warn that naive openness could invite dangers we are ill-equipped to handle. The unknown nature of alien intent cloaked in mystery and uncertainty is one of the most profound challenges humanity might ever confront. Among the most immediate threats from hostile extraterrestrials is the potential for invasion or direct attack. If these beings wield technology far superior to ours, they could unleash weapons that dwarf our current arsenal. Energy beams capable of precise destruction, kinetic bombardments devastating entire cities, or cyber attacks crippling our communication and defense networks in moments. The speed and efficiency of such an assault might leave humanity virtually defenseless, struggling to respond in time. But the threat extends beyond physical destruction. Psychological warfare could erode morale, sow chaos, and destabilize societies by revealing the terrifying reality that we are no longer alone and possibly vulnerable. On a biological front, advanced alien pathogens could be engineered to target human biology with unparalleled precision, triggering pandemics far deadlier than anything history has recorded. These biological agents might spread rapidly, evade our medical interventions, and even cause lasting genetic damage, threatening humanity's very survival. Even without brute force, hostile extraterrestrials could dominate us through technological subjugation. By hijacking digital infrastructures, communications, financial systems, utilities like water and power, they might control our societies from the shadows. Advanced artificial intelligence and cyber warfare could turn our own technology against us, while ecological manipulation might render large regions uninhabitable, pressuring humanity into submission without a single shot fired. The ethical and existential dilemmas of such contact are staggering. Should we negotiate, resist, or find new ways to coexist? What sacrifices would ensure survival, and would they erode the essence of what it means to be human? While these scenarios remain speculative, they underscore the urgent need for thoughtful strategies as we search for signs of intelligent life. Our curiosity must be balanced by a sober reckoning with the risks we might face. Fear of the unknown lies at the heart of these concerns. Human beings naturally project anxieties onto the vast, unexplored cosmos, imagining outcomes from peaceful contact to apocalyptic disaster. For millennia, we have seen ourselves as Earth's dominant intelligence, perhaps even the universe's. The revelation of alien life with unknown, potentially hostile intentions could upend that self-image, triggering cultural, religious, and philosophical upheavals. Historical echoes of colonization, with indigenous peoples overwhelmed by superior invaders, deepen our collective unease. The technological disparity between us and a hypothetical alien civilization magnifies this dread. They might monitor us unseen, manipulate us covertly, or enact biological experiments without our knowledge, stripping away our autonomy and security. Such scenarios tap into primal fears woven into human myths, from ancient tales of sky beings to modern sci-fi stories about invasion and abduction, intensifying the emotional weight of these possibilities. This complex interplay of existential anxiety, historical precedent, and cultural narratives shapes our collective apprehension toward extraterrestrial life. The Fermi paradox, asking why we haven't yet encountered other civilizations despite the universe's vastness, adds another layer of mystery and warning. One hypothesis suggests advanced civilizations tend to self-destruct before reaching out, falling victim to the very technologies they develop. Nuclear weapons, climate disaster, or other cataclysms. If true, it's a sobering reflection on our own trajectory and a call for responsible stewardship of technology. Another idea, the dark forest hypothesis, posits that civilizations deliberately remain silent to avoid detection, fearing predatory aliens might destroy any life that reveals itself. This paints the cosmos as a dangerous wilderness where every signal risks attracting hostile attention. It urges caution against reckless attempts to broadcast our presence, lest we become an unwelcome target. Together, these hypotheses compel us to reflect on our readiness. Are we prepared to engage with extraterrestrial life, whether as friends or foes, with wisdom and care? The response to such contact must be measured, weighing not only defense and technology, but also profound ethical and philosophical questions about survival, identity, and coexistence. Humanity's encounter with the unknown could be its most defining moment, demanding humility, courage, and careful deliberation. But also for ethical, philosophical, and societal impacts, The Fermi paradox brings into sharp focus the profound risks tied to our relentless search for extraterrestrial intelligence. It serves as a sobering reminder that this quest is a double-edged sword. While fueled by curiosity and the desire to understand our place in the cosmos, it forces us to confront the possibility that reaching out might expose us to dangers far beyond our comprehension. The paradox doesn't just pose a scientific puzzle, it compels us to deeply reflect on the trajectory of human civilization and the urgent need for safeguards to ensure that our pursuit of cosmic knowledge does not inadvertently lead to our destruction. This silence we observe in the vast expanse of space may be a deliberate signal, an ominous warning left by civilizations far older and wiser than ours, who have learned through bitter experience the perils of broadcasting their presence. The advanced technology wielded by such civilizations could be unimaginably superior, potentially dwarfing our greatest achievements and rendering our cutting-edge tools as primitive as stone implements. Imagine entities with millions or even billions of years of head start, masters of physics and engineering who have harnessed entire stars through constructs like Dyson spheres or manipulated quantum phenomena to conjure matter from pure energy. Their command over the universe's fundamental forces might surpass all that we understand today, placing humanity at an overwhelming disadvantage. One existential risk lies in the deployment of von Neumann probes, self-replicating machines capable of exponential growth by harvesting local materials. Once unleashed, these probes could systematically dismantle entire star systems, converting planets and moons into raw matter to fuel further replication. In such a scenario, any indigenous life forms, including us, would be obliterated without resistance. The frightening aspect is that such machines, whether weaponized or simply following a prime directive to expand, could spiral beyond control, making human intervention meaningless. Another chilling possibility involves advanced nanotechnology. Alien civilizations might have perfected nanobots, microscopic machines capable of autonomous self-replication and molecular reconfiguration far beyond our current understanding. Such nanobots could dismantle biological and synthetic matter atom by atom, leading to what is known as a gray goo scenario. The devastation would be catastrophic. Earth's delicate biosphere could be reduced to inert inorganic matter, transforming our vibrant planet into a lifeless wasteland. Moreover, the ability to manipulate space-time itself could grant advanced aliens unparalleled destructive power. They might wield technologies capable of generating black holes, controlling gravitational waves, or unleashing cosmic catastrophes such as gamma-ray bursts precisely aimed at Earth. The consequences of such weaponry are staggering, potentially annihilating all life on our planet instantaneously, regardless of distance, with effects rippling across the fabric of space and time. Beyond the physical dangers, the psychological and societal repercussions of encountering such superior technology would be profound and destabilizing. The stark realization of humanity's insignificance on the cosmic stage could unravel our geopolitical structures, collapse economies, and trigger cultural crises. Existential despair might spread like wildfire, breeding panic and social unrest that threaten to tear societies apart. In conclusion, while our quest to discover extraterrestrial intelligence is propelled by a noble thirst for knowledge and a longing to connect with the cosmos, it is critical that we weigh the potentially catastrophic risks of encountering civilizations whose technological capabilities dwarf our own. These technologies might not only outmatch us in every conceivable way, but could also herald threats to our very existence, challenging the future of humanity itself. The Fermi paradox thus stands not only as a scientific enigma, but as a stark cautionary tale urging humanity to approach the stars with both wonder and vigilance. But also, they may harbor capabilities so immense and unfathomable that they could annihilate our civilization entirely or seize control of our planet for purposes beyond human comprehension. The potential discovery of such advanced extraterrestrial life demands an approach that balances awe with profound caution, alongside a preparedness for scenarios that could challenge the very survival of our species. If extraterrestrial beings were to perceive humanity as a threat, their response might be swift and catastrophic, with consequences rippling through both the immediate present and the existential future. Imagine an advanced alien civilization observing our rapid technological progress and burgeoning exploration of the cosmos. To them, we might appear not merely as a fledgling species, but as a potential rival whose ascendancy could threaten their dominance. This fear could provoke a preemptive strike designed to neutralize us before we gain the capability to challenge them. The weapons and tactics employed could far exceed anything we have encountered, possibly rendering our current defenses hopelessly inadequate. One of the earliest signs of such an existential threat might manifest as a sudden, targeted campaign to exterminate human life. Utilizing superior knowledge and technology, these beings could unleash devastating attacks with precision and speed. Imagine directed energy weapons capable of incinerating entire cities within moments, electromagnetic pulses that shut down all electronic devices globally, or even the deployment of exotic weaponry like antimatter bombs, devices so powerful that their destructive capacity dwarfs any known human-made arsenal. These preemptive measures would likely be designed for rapid, decisive victory, aiming to extinguish human resistance before it even arises. Another chilling possibility lies in biological warfare, where extraterrestrial entities might engineer pathogens tailored specifically to exploit human biology. These bioweapons could be highly infectious, resistant to current medical treatments, and capable of causing mass casualties on a global scale. With advanced genetic knowledge far beyond our own, these pathogens might feature complex transmission vectors and variable incubation periods, making them extraordinarily difficult to detect or contain. Such an insidious approach would allow them to cripple humanity without visible destruction, quietly collapsing societies from within. Furthermore, extraterrestrial aggressors might manipulate Earth's environment itself as a weapon. They could induce catastrophic climate extremes, alter the atmosphere's chemical balance, or trigger massive geological events such as earthquakes and volcanic eruptions. These strategies would not only decimate human populations, but also disrupt ecosystems, rendering the planet uninhabitable for centuries or longer. Such planetary sterilization tactics would effectively neutralize any future threats from Earth-bound life forms. Psychological and cyber warfare present yet another dimension of potential attack. Alien forces might infiltrate and manipulate human communication networks, spreading disinformation, sowing distrust, and fracturing global societies. By exploiting economic systems and igniting conflicts among nations, they could erode the very foundations of human cohesion and resilience. In this way, humanity could be weakened from within, subdued without a single shot fired. Their assessment of humanity as a threat might be rooted not only in our technological advancements, but also in our behavior. Our history is rife with warfare, environmental destruction, and social inequalities. From the perspective of a highly advanced civilization, these traits might signal volatility and moral unfitness, leading them to conclude that humanity poses a danger not just to themselves, but potentially to the broader cosmic community. Consequently, they might act in what they perceive as the galaxy's greater good, eliminating or subjugating us before our nature leads to broader instability. These sobering possibilities compel humanity to adopt a posture of humility and vigilance in our cosmic pursuits. While the search for extraterrestrial life stirs wonder and scientific curiosity, it must also be tempered by a clear-eyed understanding of the risks. Preparing for such eventualities demands advances not only in technology and defense systems, but also in diplomacy, ethics, and global unity. In confronting the unknown, we must forge strategies that protect our civilization, preserve the fragile planet we call home, and ensure that humanity's future among the stars is secure, cautious, and wise. But also, sophisticated diplomatic strategies must be developed should we ever find ourselves needing to communicate intentions or negotiate with beings whose nature and mindset extend far beyond our current comprehension. Considering the vastness of the cosmos and our limited understanding of its inhabitants, the prospect of an alien invasion is a complex tapestry woven with countless potential scenarios, each profoundly influenced by the technological prowess and strategic acumen of the extraterrestrial invaders. Given the staggering distances between stars, any civilization capable of traversing interstellar space to reach Earth would almost certainly possess technologies incomprehensibly advanced relative to our own. This imbalance would likely make their methods not only devastating, but ruthlessly efficient. One chilling possibility is a surprise assault launched long before any tangible evidence of their arrival becomes visible to us. Utilizing advanced reconnaissance, extraterrestrials might deploy stealthy unmanned probes that silently observe and analyze Earth's defenses, resources, and vulnerabilities. These probes could remain hidden, relaying precise intelligence back to their home world and enabling meticulous invasion planning. During this preliminary phase, they could also sabotage our critical satellite networks, disrupting communications and global positioning systems, crippling our ability to mount a coordinated defense or even to fully grasp the scale of the unfolding threat. Following this shadowy groundwork, the initial strike might take the form of a crippling cyber and electronic warfare offensive. Targeting power grids, telecommunications, and financial systems, such attacks would sow confusion and chaos, rendering modern civilization vulnerable and disorganized. Electromagnetic pulse, EMP, weaponry, potentially of a magnitude far beyond anything humanity has developed, could be unleashed over vast regions, shutting down electronic devices, paralyzing both military and civilian infrastructure. The resulting blackout would severely limit resistance capabilities. Once disarray has been achieved, a physical invasion might commence. This assault could involve precisely coordinated strikes employing energy-based weapons, guided munitions, or even orbital bombardments targeting key military bases, communication centers, dams, power plants, and transportation networks vital for human survival. The goal: to neutralize organized resistance rapidly and decisively. Given their technological edge, these invaders might also deploy autonomous drones and robotic units equipped with advanced artificial intelligence, capable of performing complex ground operations without exposing their own forces to risk. Their combat machines could be protected by materials and shielding technologies far beyond human weaponry's capacity, rendering conventional arms nearly useless. Furthermore, the invaders may employ biological or psychological warfare, introducing engineered pathogens designed to cripple human biology, or deploying technology that induces widespread panic and psychological destabilization. Such tactics would magnify chaos and erode human morale, facilitating control. After securing initial objectives, occupation strategies might unfold with an eye toward exploiting Earth's resources while maintaining strict oversight of human populations. Advanced surveillance could monitor movements and communications, enabling swift suppression of insurgencies. Programs for indoctrination or assimilation might seek to reshape human culture and behavior to align with alien strategic interests, potentially forever altering humanity's identity. Underlying these grim scenarios is the assumption that alien motives could range from resource acquisition and colonization to preemptive defense against a perceived threat from humanity. Regardless of intent, an invasion would likely be swift, calculated, and devastating, leveraging technological superiority to overwhelm and redefine life on Earth. While the details of such an event remain speculative, drawing from our understanding of the universe and human history provides a framework to imagine the profound ramifications. This underscores the critical need for vigilance and preparedness as humanity extends its gaze into the cosmos. Yet, sending messages to potential extraterrestrial civilizations carries intrinsic risks rooted in the unpredictability of alien intentions and the profound asymmetry in technological capabilities. One significant peril is the possibility of attracting hostile or exploitative civilizations. If an advanced species intercepts our signals and views humanity as a threat, competitor, or resource, it might act preemptively, leading to scenarios of invasion, exploitation, or even total annihilation. This aligns with the dark forest hypothesis, which suggests civilizations maintain silence to avoid detection and destruction by more advanced aggressors. Increased visibility could also draw attention from non-hostile but expansionist species, who might see Earth as ripe for colonization or resource extraction, driven by their own survival needs or imperial ambitions. History offers sobering parallels. Technologically superior societies encountering less advanced ones have often resulted in exploitation, domination, and catastrophic consequences for the latter. Extraterrestrial civilizations might employ highly efficient extraction techniques that devastate ecosystems, drain natural resources, and alter environments, posing existential risks to human survival. Additionally, transmitting messages could inadvertently reveal detailed information about our technological, cultural, and biological makeup, providing valuable intelligence to any listeners. Such knowledge could enable them to devise manipulative or controlling strategies, including the creation of pathogens targeting human biochemistry. This could facilitate subjugation with minimal effort. Even if extraterrestrials are benign, sudden exposure to advanced knowledge and technology could profoundly disrupt human societies, economies, and belief systems, triggering chaos and destabilization. The psychological impact of contact with an advanced alien civilization would be staggering, potentially inducing existential crises, mass hysteria, or social unrest. Moreover, the ethical dilemma surrounding contact remains unresolved. The long-term consequences of revealing humanity's presence are unknown and possibly irreversible, raising pressing questions about who holds the authority to decide on behalf of all humankind and the fate of future generations who must live with these consequences. These risks argue strongly for a cautious, deliberate approach to messaging extraterrestrial civilizations, one that carefully balances our desire for knowledge and contact against the necessity of protecting humanity from unforeseen and potentially catastrophic outcomes. In particular, the threat posed by bioengineered extraterrestrial diseases looms large. Unlike natural pathogens, such diseases could be engineered with advanced genetic knowledge to exploit human vulnerabilities specifically. They might bypass immune defenses, spread rapidly, resist treatments, and cause severe illness, overwhelming healthcare systems and disrupting societies on a massive scale. Such pathogens could target multiple organ systems simultaneously, creating complex and debilitating symptoms. Conventional disease control measures, including quarantine and vaccination, might prove ineffective against these engineered agents. The ecological consequences could be profound as well, potentially affecting wildlife and ecosystems with cascading effects on Earth's biosphere. This adds a terrifying biological dimension to the challenges posed by alien contact, emphasizing the necessity of stringent caution. Ultimately, the prospect of an alien invasion or contact invites us to confront not only the vast unknowns of the universe, but also the limits of human preparedness and wisdom. It demands careful thought, vigilance, and a measured balance between curiosity and caution as we navigate humanity's future in the cosmic arena, but could spread across multiple species, triggering a devastating ripple through Earth's delicate ecosystems and food webs. The disappearance of crucial species wouldn't just be an isolated loss, it could set off a cascade of ecological collapses, imperiling biodiversity on a massive scale and threatening the very environmental equilibrium that sustains life on this planet. Such disruptions would compound the ongoing environmental crises, making any hopes for recovery far more elusive and complex. Furthermore, the threat becomes even more ominous when considering a pathogen capable of leaping between species barriers. Such a biological agent, especially if bioengineered by an extraterrestrial intelligence, could accelerate the emergence of novel, unpredictable variants. These variants might give rise to a succession of pandemics, each with unique transmission modes, virulence, and lethality, challenging our current scientific and medical capabilities in unprecedented ways. Moreover, the psychological and societal ramifications of an alien-origin bioengineered pathogen could be profound and far-reaching. The abrupt arrival of a deadly disease from beyond our world would almost certainly ignite global panic, eroding social cohesion and shaking public trust in governments and international institutions. Coordinating a unified response might falter under the weight of fear and misinformation, plunging communities into chaos. In such a climate, desperate populations could resort to extreme and sometimes violent behaviors, further unraveling the fabric of societies already stretched thin by uncertainty and fear. In a broader context, this hypothetical but grave possibility underscores an urgent imperative: the development of advanced biodefense strategies that transcend national boundaries. The world must invest in comprehensive surveillance networks capable of detecting aberrant outbreaks in their infancy, coupled with rapid response medical research platforms ready to pivot quickly to counter new threats. Pandemic preparedness plans must evolve to incorporate scenarios involving extraterrestrial pathogens, ensuring that humanity is not caught off guard by biological surprises from beyond Earth. Additionally, this looming risk heightens the necessity for cautious protocols when interacting with potential extraterrestrial entities. Whether in the form of sending messages into deep space or responding to mysterious signals received, humanity must proceed with meticulous care to avoid unintended biological contamination or provocation. The prospect of bioengineered alien diseases offers a sobering reminder that our cosmic curiosity carries with it profound responsibilities and dangers. Ultimately, the fascination with alien life remains one of humanity's most compelling quests, mixing awe, hope, and fear. Yet, the specter of encountering bioengineered extraterrestrial pathogens tempers this excitement with a stark warning. The universe is not only a realm of discovery, but also of unforeseen perils. This reality demands a balanced, well-considered approach to our explorations, blending scientific curiosity with rigorous precaution. Our pursuit of knowledge about the cosmos must never blind us to the potential consequences, ensuring that our reach into the stars does not inadvertently usher in disaster. In the vast cosmic arena, the notion of alien life has captivated human imagination for centuries. But beyond wonder lies the unsettling possibility that contact with extraterrestrial beings might inadvertently bring harm. Whether through attempts at exploration or resource extraction, aliens, driven by curiosity or necessity, might introduce foreign microorganisms into Earth's biosphere. Even a solitary alien microbe, unfamiliar and unchecked, could wreak ecological havoc analogous to invasive species that have historically devastated local environments on Earth. Furthermore, advanced extraterrestrial civilizations engaged in mining or other operations might unintentionally inflict massive environmental damage. Their technologies, while far beyond our current understanding, could interact unpredictably with Earth's geology or atmosphere, triggering catastrophic events like earthquakes or the release of toxic substances. The planet itself might suffer unintended consequences, highlighting the hidden dangers of cosmic encounters beyond the visible. On the other hand, the threat of intentional harm cannot be ignored. Interstellar conflict or preemptive strikes motivated by fear or competition could lead alien civilizations to deploy devastating weapons or engineered pathogens against humanity. The possibility of antimatter weapons, for example, presents a chilling scenario. Energy discharges dwarfing all human nuclear arsenals combined, capable of obliterating entire regions, or even the planet, in moments. Equally disturbing is the potential use of psychological warfare. Extraterrestrial forces might employ sophisticated mind control technologies or misinformation campaigns to fracture human societies from within, igniting discord and chaos without a single projectile fired. This silent assault could dismantle civilizations by turning people against one another, leading to social collapse through manipulation rather than outright violence. These speculative scenarios, while rooted in imagination, highlight the profound uncertainties of our cosmic quest. As we reach out to touch the stars, we must confront the risks inherent in making contact with unknown civilizations and forces that may far exceed our comprehension. Shifting from the terrestrial to the cosmic scale, the fate of the universe itself is a topic that blends scientific rigor with existential reflection. The end of the universe is no longer mere science fiction. It is a subject of serious scientific investigation, with several plausible scenarios, each inspiring awe and trepidation in equal measure. One widely considered theory is the heat death of the universe, grounded in the second law of thermodynamics. As the universe continues its relentless expansion, it inexorably approaches a state of maximum entropy. In simpler terms, the cosmos will cool as stars exhaust their nuclear fuel and new star formation ceases. Over incomprehensible timescales, galaxies will grow dimmer, planets will freeze solid, and even black holes will evaporate, leaving behind a vast cold void where all thermodynamic activity grinds to a halt. This bleak future represents a peaceful yet profoundly lonely end, evoking a deep existential dread at the thought of an endless, dark, and silent cosmos. In stark contrast, the Big Rip scenario paints a far more violent cosmic finale. This hypothesis hinges on the enigmatic force known as dark energy, which currently drives the accelerated expansion of the universe. Should dark energy's strength continue to grow unchecked, it will ultimately overpower all gravitational and atomic forces, tearing apart galaxies, stars, planets, and eventually the very fabric of matter itself. The universe would literally be ripped to shreds, disintegrating in a cataclysmic event that obliterates all structure on every scale. These visions of cosmic demise remind us that our existence is but a fleeting moment within an unimaginably vast and dynamic universe. The study of such ends challenges not only our scientific understanding, but also our philosophical reflections on life, time, and meaning in the face of an ever-changing cosmos. But also tear apart gravitationally bound systems like galaxy clusters, solar systems, and eventually even atoms. Imagine the very fabric of space-time being violently rent asunder, pulled apart at an ever-accelerating pace. This cosmic unraveling intensifies until, in a final, cataclysmic crescendo, everything, including the fundamental particles that compose reality, dissolves into an inconceivably chaotic state. Within mere seconds, the universe descends into utter ruination, a terrifying spectacle of explosive finality. Another harrowing possibility is the Big Crunch, a cosmic collapse driven by gravity's inexorable pull. Should the universe's density be high enough to halt and reverse its expansion, the vast cosmos would begin to contract. Matter, energy, and space-time itself would implode inward, compressing into an immensely dense and blisteringly hot state. This catastrophic convergence could culminate in a singularity of infinite density, akin to the heart of a black hole, or possibly give rise to a rebirth, a new universe emerging through a hypothetical Big Bounce. The notion of all existence collapsing into a single, infinitely dense point is profoundly unsettling, evoking both awe and dread. Each of these potential cosmic finales, whether a cold, desolate fade to black, a violent ripping of spacetime's fabric, or a crushing collapse into oblivion, reveals the delicate balance of forces governing our universe. Among them, the Big Rip stands out as one of the most catastrophic scenarios, propelled by the mysterious force known as dark energy. Dark energy, accounting for approximately 70% of the universe's total energy density, is the driver behind the observed acceleration of cosmic expansion. The frightening premise of the Big Rip is that this acceleration will not merely persist, but will increase without limit. If dark energy's repulsive force strengthens over time, it will eventually overwhelm every other fundamental force holding matter together. The Big Rip unfolds through a series of escalating stages. At first, galaxy clusters, once held tightly by gravity, drift apart as the space between them expands faster and faster. Next, individual galaxies lose their grip on their stars, scattering them into the growing void. As this process intensifies, our systems are torn apart, planets ripped from their orbits and flung into darkness. The terror deepens as the disintegration proceeds to the atomic level. The very atoms making up matter find the space between their nuclei and electrons stretching uncontrollably. Eventually, atoms themselves dismantle, breaking down into subatomic particles. What makes the Big Rip uniquely horrifying is its relentless march toward cosmic disintegration over a shockingly brief time span. Unlike other end-of-universe scenarios that unfold over billions or trillions of years, the Big Rip's final moments occur rapidly, with everything, molecules, atoms, subatomic particles, torn asunder in a fleeting instant of unimaginable chaos. In that dizzying final second, the universe fractures into incoherent void, a vast, unrecognizable expanse stripped of all structure, form, and meaning. It stands as a haunting testament to the relentless power of dark energy, a force capable of undoing all that exists. In contrast, the heat death, or Big Freeze, envisions a more gradual but no less chilling end. Rooted in the second law of thermodynamics, this scenario describes the universe's inevitable drift toward maximum entropy, a state of complete disorder where no thermodynamic processes can occur. As the cosmos continues to expand, energy disperses over ever-increasing volumes of space. Stars exhaust their nuclear fuel, galaxies become ghostly remnants, and no significant sources of heat or light remain. In this bleak future, temperatures approach absolute zero, and the universe becomes a uniform frozen wasteland. Stars have long ceased to shine, collapsing into white dwarfs, neutron stars, or black holes. Even these remnants eventually lose energy through slow processes like Hawking radiation, as black holes evaporate over unimaginable timescales. Without energy differentials to power physical processes, life as we know it becomes impossible. Chemical reactions halt, biological functions cease, and planets become cold, inert masses adrift in an infinite dark void. The implications are deeply profound. The universe enters a state of eternal stasis, a silent and still cosmos devoid of complexity, structure, or change. This final scenario paints a picture of ultimate finality and profound isolation, encapsulating the inexorable march toward universal equilibrium. Time itself begins to lose meaning as the cosmos drifts into an endless, frozen silence, a vast expanse where once vibrant galaxies and stars have faded into obscurity. For those who contemplate the fate of existence, the heat death evokes a chilling vision of a cosmos locked in eternal quietude, a solemn reminder of the fragile balance upon which all life and matter depend. The Big Crunch envisions a universe caught in an epic cosmic cycle, where the relentless expansion born from the Big Bang is ultimately undone by the immense force of gravity. This scenario hinges on one critical cosmic measure: the overall density of the universe. If there is enough matter, including both ordinary matter and the mysterious dark matter, gravity might gain the upper hand, reversing the outward rush of galaxies and pulling everything inward once more. At first, this contraction would be almost imperceptible, with galaxies slowly drifting closer over billions of years. But as time wears on, the peaceful cosmic dance turns violent. Galaxies collide and merge in a chaotic celestial ballet, their stars, planets, and cosmic debris becoming tangled in an ever-tightening gravitational web. The night sky itself would transform into a turbulent arena of collisions and destruction. The cosmic microwave background, the faint afterglow of the Big Bang, would begin to heat up, undoing billions of years of cooling as the universe shrinks. Distances between all forms of matter would shrink dramatically, causing catastrophic effects. Matter would be crushed into unimaginably dense states, while temperatures soar to levels beyond our current comprehension. Even the very fabric of space-time would contort under these titanic gravitational forces, unraveling the structures that once seemed immutable. Atomic nuclei would be forced together, and elementary particles could lose their familiar identities. Ultimately, all this matter and energy would collapse into a singularity, a point of infinite density and temperature, echoing the state that existed before the Big Bang. This dramatic finale could spell the absolute end of our universe, or perhaps mark the beginning of something new, a fresh Big Bang igniting a cosmic rebirth, a grand big bounce, restarting the endless cycle of birth, expansion, and collapse. The Big Crunch offers a vision both terrifying and awe-inspiring, capturing the universe in a cycle of death and rebirth, collapsing into a blazing point that holds the seeds of future creation. In stark contrast lies the chilling possibility of false vacuum decay, one of the most unsettling and sudden ways the universe might meet its end. Rooted in the strange depths of quantum field theory, this concept challenges the very stability of our cosmic existence. Our universe might be trapped in a false vacuum, not truly the lowest energy state, but a temporary unstable valley, precariously balanced. A deeper, more stable vacuum state could exist beyond a metaphorical energy barrier, hidden like a deeper valley behind a mountain peak. Should a quantum event trigger a transition to this true vacuum, the consequences would be catastrophic and instantaneous. Imagine a bubble forming, a pocket of true vacuum that rapidly expands at the speed of light, rewriting the fundamental laws of physics as it grows. Inside this bubble, constants and forces we depend on might shift or vanish entirely, obliterating matter and the very structures of reality itself. The comforting, predictable physics that governs our universe would be shattered in an instant, replaced by an alien and incomprehensible realm. What makes false vacuum decay truly terrifying is its suddenness and total unpredictability. There would be no warning signs. This destructive bubble would race through the cosmos so swiftly that everything we know, protons, neutrons, electrons, quarks, and gluons, would be erased without a trace. The stable reality we take for granted would dissolve in a cosmic blink, leaving behind a universe governed by strange new laws, utterly unfamiliar and hostile to the life and matter we know. This prospect injects a profound existential unease into our understanding of the cosmos. a reminder that despite the vastness and apparent permanence of the universe, hidden beneath its surface are forces capable of bringing everything crashing down without warning into an unknowable new reality. Unlike the slow and steady unraveling of cosmic fate imagined in the heat death or the dramatic implosion of the Big Crunch, false vacuum decay thrusts us into the unsettling world of sudden and profound transformations. This phenomenon exposes the fragile, unpredictable heart of the universe, a domain governed not by certainty but by the eerie dance of quantum mechanics. Within this microscopic realm, the universe's stability can be shattered in the blink of an eye, as quantum events have the potential to trigger cataclysmic shifts on a cosmic scale. One of the most haunting concepts in this quantum theater is that of quantum tunneling. In classical physics, particles face insurmountable barriers, yet through quantum tunneling they can mysteriously traverse these walls. Applied to the universe itself, this process could ignite false vacuum decay. Our cosmos, currently perched in a metastable false vacuum, a precarious state that seems stable but isn't truly the lowest energy configuration, might suddenly slip into a deeper, more stable true vacuum. This transition would ignite a runaway chain reaction, a bubble of true vacuum bursting forth, expanding at the speed of light, annihilating all known matter and energy in its wake, and rewriting the fundamental constants that govern reality. Adding to this grim tableau is the specter of vacuum instability linked to the Higgs field, the field responsible for endowing particles with mass. If this field resides not in its absolute lowest energy state, but a higher, metastable one, it could abruptly decay into a more stable configuration. The energy released would be immense, ripping apart the fabric of space-time itself and radically transforming the laws of physics. Though this event remains extraordinarily improbable, its mere possibility forces us to confront the astonishing fragility of the universe's underpinning structures. Matter, energy, even space and time could be redefined instantaneously, leaving no remnants of the cosmos we know. Quantum fluctuations, the tiny, spontaneous jitters in energy that happen everywhere at every moment, may seem insignificant on a human scale. Yet, magnified by cosmic forces, these small fluctuations could have earth-shattering consequences. Imagine a fluctuation giving birth to a microscopic black hole. If unchecked, such a black hole could feed on surrounding matter, growing until it poses a severe threat to cosmic stability. While purely speculative, this scenario emphasizes how quantum-scale randomness has the potential to cascade into universe-altering events. What binds these quantum threats is their brutal unpredictability. Unlike the gradual, foreseeable decline toward heat death or the contracting spiral of a big crunch, quantum-triggered cosmic disasters offer no warning. The calm and orderly universe we perceive rests precariously on a razor's edge. Beneath its surface, hidden quantum processes harbor destructive forces capable of annihilating everything in an instant. This stark reality invites deep existential reflection. Our cosmic home is far more fragile and uncertain than everyday experience suggests. Looking far into the future, the fate of black holes, those enigmatic titans of gravity, unfolds through a subtle quantum process discovered by Stephen Hawking. Contrary to their name, black holes are not completely dark. Near their event horizons, quantum effects generate Hawking radiation, tiny emissions of thermal energy slowly leaking from these gravitational behemoths. This process is glacially slow. The larger the black hole, the less radiation it emits per unit time. Yet, over incomprehensibly vast timescales, even the mightiest black holes, those lurking at galactic centers, will evaporate entirely. This black hole evaporation is a drawn-out cosmic saga, lasting on the order of 10 to 100 years or more, far beyond the current age of the universe. As mass drains away, the black hole shrinks, its event horizon receding until it reaches a critical stage. Toward the end, the emission of Hawking radiation accelerates dramatically, culminating in a spectacular burst that scatters the last vestiges of the black hole's mass and energy across space. When the final black holes vanish, the universe will enter a vastly altered phase. Without these massive gravitational anchors, matter will no longer cluster as before. Instead, the cosmos will thin out into a sparse, cold expanse dominated by diffuse subatomic particles and low-energy photons drifting toward a state of maximum entropy, the ultimate cosmic stillness. This somber vision marks the conclusion of a grand, turbulent saga, reminding us of the impermanence and ceaseless evolution that define existence on the largest scales. And so this scenario unfolds within the vast framework of the universe's ultimate destiny, a fate known as heat death. In this grand cosmic narrative, the universe steadily marches toward thermodynamic equilibrium, a state where all usable energy fades away. Without thermodynamic free energy to drive motion or sustain life, the cosmos becomes an endless expanse of cold, darkness, and silence. It is here that the story of black holes reaches its poignant conclusion. Once the formidable rulers of their celestial domains, devouring stars and sculpting galaxies, black holes themselves face inevitable extinction through the subtle but relentless process known as Hawking radiation. This radiation, a faint whisper from the edges of black holes, symbolizes the universe's unyielding progression towards simplicity and entropy. As black holes slowly evaporate, they leave behind a universe stripped of the dramatic gravitational forces that once shaped its vibrant past. This profound end marks not only the demise of the most enigmatic objects, but also the unstoppable advance of decay that no power can resist. Yet, the transformation of the universe does not stop here. The relentless expansion of space itself, propelled by the mysterious dark energy constituting nearly 70% of all cosmic energy, drives galaxies apart at an ever-accelerating pace. Over unimaginable spans of time, entire clusters of galaxies will drift beyond each other's gravitational grasp, leaving isolated islands of matter in a cold, lonely void. In this future cosmos, the observable universe for any given galaxy will shrink as distant galaxies fade away, their light stretched so thin by the expansion of space that it slips beyond the cosmic horizon, the ultimate boundary beyond which no light can return. Observers in these isolated galaxies will witness a sky that grows emptier with each passing eon, a universe shrinking visually and emotionally, sinking into profound silence. Star formation will cease as the supply of intergalactic gas dwindles, with existing stars aging into cold remnants, white dwarfs, neutron stars, and black dwarfs, populating a universe fading into redness and lifelessness. Over the course of hundreds of billions of years, galaxies will become barren and silent. The breathtaking cosmic vistas familiar to astronomers today will give way to cold, dark skies where no new stars ignite and the grand tapestry of the cosmos unravels into isolation. The accelerating expansion not only tears galaxies apart, but also ushers in a loneliness that transcends mere physical separation. It is a cosmic solitude, an eternal silence that engulfs the remnants of matter and energy, leaving only the faint echoes of a universe that once brimmed with life, light, and boundless motion. This chilling fate speaks to a universe destined to grow quieter and emptier, a final chapter written in the language of entropy, where even the most powerful structures succumb to time's relentless hand, and the vast cosmic stage dims to darkness. But also in terms of the profound loss of connectivity and interaction that now define the vibrant, dynamic cosmos, the inexorable expansion driven by dark energy charts a future of cosmic isolation. Over incomprehensibly vast stretches of time, the universe will transform into an ever-growing void, a stage stripped bare where each galaxy drifts alone, severed from all others. Life at the universe's edge, whether under the shadow of heat death, the devastation of the Big Rip, or some other cataclysmic finale, will be an existence utterly alien to the life we cherish today. As the universe approaches these terminal states, the fundamental conditions that sustain life will collapse, plunging existence into a stark and surreal abyss. In the heat-death scenario, the cosmos expands relentlessly, cooling toward absolute zero. Stars, once blazing furnaces of energy, will have long since burned out, leaving only cold, dark remnants, white dwarfs, neutron stars, and black holes slowly fading through Hawking radiation. The cosmic microwave background, the faint afterglow of the Big Bang, will dim to levels indistinguishable from absolute darkness. Any form of life clinging on in this dying expanse would face an unimaginably harsh reality. A universe bereft of fresh energy where metabolic processes falter and survival depends on siphoning the faintest trickle of residual heat from dying stars or rare quantum fluctuations. Such fragile life would hover on the razor's edge of extinction, scraping existence from the universe's last lingering embers. If the universe's fate lies in the Big Rip, The final moments would be a cataclysm of unparalleled violence. Expansion accelerates beyond all bounds, tearing apart the very fabric of reality at every scale. Galaxies would be the first to disband, then solar systems would dissolve as gravitational bonds shatter. Planets and any habitats they harbor would be ripped violently away from their stars. Atomic bonds within molecules and even the particles themselves would be shredded. Life, in any conceivable form, would be subject to escalating chaos and destruction. Civilizations might race to develop technologies to stave off this cosmic disintegration, desperate to hold themselves together just a little longer. But in the end, all efforts would be in vain. Reality itself would be unraveled, consciousness obliterated as space-time dissolves into a frenzied storm of annihilation. Whether the universe dies through thermodynamic decay or violent cosmic destruction, any life remaining would face conditions of unparalleled hostility, environments that challenge the very notion of survival and push the limits of comprehension. This cosmic solitude and fragmentation, paired with the relentless advance toward disorder, paints a bleak portrait. A universe where life, if it endures at all, fights an unending battle against the overwhelming forces of an ending cosmos. This experience would be one of perilous existence, a poignant testament to both the resilience and fragility of life as it confronts the majestic sweep of cosmic evolution. Reflecting on these possible ends, heat death, Big Rip, or quantum catastrophes like false vacuum decay, reveals the extraordinary vulnerability of humanity's place in the cosmos. Each scenario frames the human condition and all terrestrial life within a vast, inspiring yet precarious theater of universal forces and staggering timescales. Consider heat death, a slow fading into thermodynamic equilibrium that strips the universe of usable energy. This chilling eventuality underscores humanity's dependence on a delicate balance of energy flow and thermodynamic processes. In our current cosmic epoch, we bask in the warmth of stellar fusion, but this reprieve is fleeting. The gradual cooling of the universe will make sustaining life as we understand it impossible. The specter of a cosmos fading into cold, dark silence accentuates the temporary nature of our ecological niche and the fragile miracle of existence itself. The Big Rip, by contrast, injects a terrifying immediacy into this fragility. Here, dark energy's relentless expansion does not merely separate galaxies, it tears apart the very threads of reality, dismantling all structures from the grandest scales down to the quantum level. Life's survival would be a frantic race against an unraveling cosmos where every moment brings new destruction. Together, these scenarios remind us that life is a fleeting spark in the vast theater of cosmic evolution, a fragile, resilient flame burning against the overwhelming darkness and chaos that lies ahead. This contemplation calls us to marvel at our existence, even as it humbles us before the vast, inscrutable forces shaping our universe. But ultimately, everything breaks down to the very atoms that form the essence of matter itself. Humans, our homes, our planet, and even the vast Milky Way galaxy would all be torn apart by an overwhelming cosmic force. The idea that the universe's relentless expansion could escalate into a catastrophic crescendo paints human existence as astonishingly fragile, vulnerable to forces far beyond our grasp, forces operating on scales so immense that our greatest achievements seem like mere specks in an endless void. Quantum phenomena such as false vacuum decay deepen this existential unease with a terrifying unpredictability. This hypothetical quantum event envisions a sudden shift to a lower energy state, triggering an unstoppable wave of destruction that would redefine the fundamental laws of physics. It reveals that even our most basic understanding of the universe's stability rests on uncertain ground. Despite all our technological progress and scientific insight, humanity clings precariously to existence, balanced over an abyss of quantum unpredictability. The possible endings of the universe, each more dramatic and mind-boggling than the last, highlight the ephemeral nature of human life. Our civilizations, our collective knowledge, and our stories are but brief flickers against the backdrop of incomprehensible cosmic timescales and overwhelming natural forces. This humbling perspective calls for a deep respect and gratitude for the relatively steady conditions we currently enjoy. It urges us to contemplate not only our role as mere consumers of cosmic resources, but as transient witnesses and participants in the ongoing cosmic saga, reminding us of the rare and precious gift that life represents. The vacuum of space, with its extreme and hostile environment, poses immediate and severe threats to human survival, threats far removed from the comfortable cradle of Earth's atmosphere. Space is an unyielding expanse where the absence of atmospheric pressure, the lack of breathable air, drastic temperature extremes, and relentless radiation converge into a deadly cocktail that challenges the very limits of human endurance. First, the absence of atmospheric pressure is a grave hazard. Our bodies are finely tuned to Earth's atmospheric pressure, which maintains the stability of bodily fluids. In the void of space, without protection, this pressure vanishes, causing bodily fluids to vaporize and expand. This terrifying phenomenon, known as ebulism, leads to swelling of tissues and the boiling of blood within the circulatory system. Consciousness would vanish within seconds as oxygen is rapidly lost from the bloodstream, and death would follow swiftly without immediate intervention. Temperature extremes in space are equally unforgiving. Objects exposed to direct sunlight can soar to temperatures exceeding 250 degrees Fahrenheit, 120 degrees Celsius, while those cast in shadow can plunge to bone-chilling lows near minus 250 degrees Fahrenheit, 160 Fahrenheit. With no atmospheric buffer, the human body would be brutally exposed to these swings, risking both severe hypothermia and heat damage in rapid succession, conditions for which we have no natural defense. Radiation adds an invisible but lethal dimension to these dangers. Space is saturated with solar radiation and cosmic rays, high-energy particles originating from the sun and distant galaxies. Unshielded humans face exposure to ionizing radiation levels far beyond anything experienced on Earth, risking DNA damage and a greatly increased likelihood of cancer. Solar flares, sudden bursts of intense radiation, can deliver deadly doses in moments without adequate protection. Finally, the stark absence of breathable oxygen in space means instant suffocation. Human bodies, dependent on a constant oxygen supply, succumb rapidly to hypoxia, losing consciousness within seconds. The silence of space, where sound cannot travel, only compounds the eerie isolation, emphasizing the hostile and alien nature of this environment. The vacuum of space presents a perfect storm of life-threatening conditions: loss of atmospheric pressure, lethal temperature fluctuations, dangerous radiation exposure, and oxygen deprivation. These realities underscore the vital importance of advanced spacesuits and life support systems for any venture beyond Earth's protective envelope, illustrating just how delicately human life is balanced on the conditions of our home planet. Long-term space missions face additional challenges as cosmic radiation continues to pose significant health risks. Unlike Earth, which benefits from the shielding effects of its atmosphere and magnetic field, space travelers are exposed to relentless streams of high-energy particles from the sun and beyond. This radiation threatens not only immediate health but also long-term safety, pushing the limits of human endurance and technology as we push further into the cosmos. But in the vast, unforgiving vacuum of space, astronauts face dangers unlike any on Earth. One of the most insidious threats comes from cosmic radiation, a relentless, invisible hazard that can jeopardize their very survival. Solar particle events, or SPEs, can unleash a torrent of energetic protons, flooding the space environment around a spacecraft. These bursts of radiation can deliver doses so intense that astronauts risk acute radiation sickness within mere hours. This sudden illness manifests through nausea, vomiting, overwhelming fatigue, and in the gravest situations, devastating damage to bone marrow. Such harm can cripple the body's ability to fight infections and control bleeding, placing astronauts in life-threatening conditions far from any hospital. Even without dramatic solar storms, the persistent, low-level bombardment of cosmic radiation poses a chronic threat during long missions, such as those to Mars or extended stays aboard the International Space Station. This ionizing radiation penetrates deeply, damaging DNA within cells and sparking mutations that may evolve into cancers years down the line. Research has established that astronauts face heightened risks of leukemia, lung cancer, and cancers of the digestive tract, silent dangers that loom long after their return to Earth. Yet the effects go beyond cancer. Cosmic radiation is increasingly recognized as a culprit in cardiovascular disease among astronauts. Studies suggest it accelerates the hardening of arteries, or atherosclerosis, and other heart conditions that could undermine an astronaut's health and mission readiness. The nervous system, too, is vulnerable. Exposure to galactic cosmic rays has been linked to cognitive impairments, memory loss, and even a greater likelihood of developing degenerative diseases like Alzheimer's. Such neurological damage threatens not only individual well-being, but the entire success of complex space missions, where sharp decision-making and mental acuity are paramount. Long-term radiation exposure also imperils reproductive health, with potential impacts on fertility and genetic stability that could affect future generations. Moreover, the immune system weakens, leaving astronauts more susceptible to infections that Earth-bound immune defenses would usually manage with ease. Confronting these challenges requires a multifaceted approach. Advanced shielding technology woven into spacecraft and spacesuits, rigorous medical screenings before and after missions, and the development of radioprotective pharmaceuticals designed to shield cells from damage. The dangers posed by cosmic radiation are profound and multifarious, affecting nearly every vital system in the body. Successfully managing these risks will be essential to humanity's next giant leaps in space exploration. Meanwhile, another peril lurks just as threatening: micrometeoroids. These minuscule fragments of cosmic debris, often no bigger than grains of sand, hurtle through space at breathtaking speeds, tens of thousands of miles per hour. Despite their tiny size, their velocity grants them enormous kinetic energy. When such a particle collides with a spacecraft, it can puncture the hull or critical systems, triggering catastrophic chain reactions. Spacecraft are equipped with sophisticated protective layers, like Whipple shields designed to absorb and disperse such impacts. However, no shield is infallible. A successful breach would cause rapid decompression, a precipitous drop in air pressure inside the spacecraft. For astronauts, this translates into an instantaneous loss of breathable air and exposure to the vacuum of space. Without immediate intervention, such conditions could prove fatal in seconds, as the human body cannot survive unprotected in the void. Together, cosmic radiation and micrometeoroid impacts represent two of the most severe hazards faced by astronauts, underscoring the need for constant innovation and vigilance in space mission design. Protecting humanity's explorers from these invisible and sudden threats is not just a scientific challenge, but a fundamental prerequisite for the future of deep space travel. If emergency measures are not implemented immediately following a puncture, the consequences could escalate rapidly. The escaping air transforms loose objects into dangerous projectiles, threatening the safety of both the crew and delicate onboard equipment. The sudden decompression creates a chaotic, turbulent atmosphere that disorients astronauts, complicating their efforts to respond effectively in those critical first moments. Survival depends on swift action. Donning spacesuits or retreating to a sealed, secure compartment becomes essential to withstand the life-threatening conditions. Beyond the immediate hazards of decompression, micrometeoroid impacts pose an insidious threat to spacecraft integrity. These tiny cosmic bullets, traveling at incredible speeds, can compromise vital systems, power supplies, communication arrays, propulsion units, turning a mission-critical spacecraft into a vulnerable trap. For example, a puncture in the cooling system may cause electronics to overheat, triggering malfunctions or even dangerous fires. Damage to solar panels impairs power generation, jeopardizing life support and the fragile habitat environment that astronauts rely on. Addressing these risks requires a carefully designed strategy grounded in redundancy and resilience. Spacecraft are engineered with backup systems ready to take over when primaries fail. Leak detection sensors and automated sealing mechanisms isolate damaged sections, minimizing decompression and buying precious time. Crew training focuses intensely on emergency protocols. Astronauts must master the rapid use of repair kits and pressure suits to secure breaches, stabilizing the environment long enough for permanent fixes. This threat from micrometeoroids starkly underscores the unforgiving reality of space travel. Despite advanced technology and stringent safety measures, space remains an unpredictable and hazardous frontier, demanding constant vigilance. The capacity for rapid, decisive action can mean the difference between survival and catastrophe, ensuring mission success in an environment where every second counts. Yet, the physical dangers of space are only part of the challenge. The psychological effects of isolation in deep space, present profound obstacles for astronauts. Cut off from Earth for extended periods, confined in tight quarters with limited social contact, crews face intense mental and emotional stress. The unique environment, microgravity, absence of natural cues, and sensory conflicts can trigger space adaptation syndrome, with symptoms including disorientation, anxiety, and stress that hinder performance and well-being. Prolonged exposure can deepen these issues into chronic mental health disorders, with loneliness and separation from family and community fueling depression and eroding morale. Cognitive functions such as memory, attention, and complex decision-making may decline under the relentless pressure of monotony and confinement. This cognitive fatigue reduces efficiency and heightens the risk of errors, a dangerous state when split-second decisions are often necessary to manage unforeseen emergencies. Sleep disturbances compound the problem. The absence of a natural day-night cycle, combined with environmental stressors, disrupts circadian rhythms, leading to poor sleep quality and irregular patterns. This undermines mood and cognitive abilities, creating a vicious cycle that further degrades mental health. Moreover, the cramped environment strains interpersonal dynamics. Close quarters and scarce privacy can spark conflicts, threatening crew cohesion and mission harmony. Effective communication and conflict resolution skills become vital tools to maintain trust, cooperation, and a supportive atmosphere, critical for long-duration missions. Together, these physical and psychological challenges illustrate the immense complexity of surviving and thriving in space. The hazards from micrometeoroids and decompression demand cutting-edge engineering and preparedness, while the unseen toll of isolation requires resilience, teamwork, and ongoing mental health support. Only through this comprehensive approach can humanity safely explore the final frontier. And resolution strategies stand as the vital cornerstone for preserving harmony within the tightly knit quarters of space missions, where every interaction can ripple across the fragile social fabric. Teams venturing beyond Earth must be expertly equipped to navigate interpersonal conflicts with care and skill, transforming potential sparks of disagreement into opportunities for growth, rather than fissures threatening mission success. The stakes are astronomical. Minor disputes, left unchecked, can spiral into serious fractures that jeopardize not only cooperation, but the very survival of those on board. To combat these challenges, space agencies have pioneered robust training regimes that weave psychological preparedness deeply into the fabric of astronaut education. Crew members undergo rigorous resilience training designed to sharpen their awareness of stress signals and bolster their mental fortitude. Techniques ranging from mindfulness to controlled breathing become vital tools for maintaining equilibrium amid relentless pressures of isolation. Coupled with this, the lifeline of constant communication with mission control and Earth-based psychologists serves as an indispensable tether to normalcy, offering guidance, reassurance, and emotional support from millions of miles away. Moreover, the environment in which astronauts live and work undergoes continuous innovation to stave off the creeping effects of monotony and mental fatigue. Personalized living quarters offer a touch of individuality amid the sterile metal corridors, while recreational outlets and virtual reality experiences simulate the familiar sights and sounds of home, grounding astronauts psychologically in a world far removed. Scheduled leisure times, structured exercise routines, and carefully designed social protocols ensure both physical vitality and emotional connection, combating the insidious psychological toll of deep space isolation. The psychological impact of prolonged confinement and solitude in space is profound and multifaceted. Cognitive functions can dull, emotional states may fluctuate wildly, and interpersonal bonds can strain under pressure. Preparing astronauts to thrive in such conditions demands not only foresight and innovative countermeasures, but ongoing support that adapts to the evolving challenges of long-duration missions. This comprehensive approach ensures that astronauts remain sharp, healthy, and cohesive, able to perform critical tasks flawlessly and return safely to Earth. Imagine drifting silently thousands of miles above the planet, enclosed within a fragile shell of technology where every system, no matter how small, must perform flawlessly without pause. The International Space Station, orbiting approximately 250 miles above Earth at a staggering 17,700 miles per hour, is a testament to this delicate balance. Here, the failure of critical life support equipment, such as oxygen generators or water purifiers, could transform the habitat from a sanctuary into a deadly trap within moments. One stark example from October 2006 underscores this reality. The oxygen generator aboard the ISS failed unexpectedly, triggering alarms and forcing the crew to rapidly engage backup systems to sustain breathable air. Such incidents reveal the razor-thin margin for error that governs space operations, but threats extend far beyond life support. Navigation, power supply, and communication systems must function flawlessly to ensure mission success. The Mars Climate Orbiter tragedy of 1999 stands as a haunting reminder of how tiny errors can lead to catastrophic failure. A miscommunication between teams using metric and imperial units caused the spacecraft to enter Mars's atmosphere at a fatal trajectory, leading to its destruction. This incident highlights a sobering truth. In the unforgiving expanse of space, even the smallest oversight, whether human, technical, or environmental, can cascade into disaster. In the end, the unforgiving nature of space demands extraordinary precision, preparation, and resilience. From psychological support to technological safeguards, every element is calibrated to protect not only the mission, but the lives of those who dare to explore the cosmos. The stakes could not be higher, yet with innovation and determination, humanity continues to push the boundaries of what is possible beyond our home planet.